The discovery of blue stragglers is a very recent one. It dates back only to 1953. Alan Sandage, an astronomer at the Carnegie Observatories in Pasadena, California, first described this type of star while observing M3, a globular cluster located some 33,300 light-years from Earth in the Hound constellation. While studying this star cluster, which is one of the largest and brightest globular clusters on record at the time, he was surprised to discover it. While carrying out photometry, he noticed in the midst of countless old stars and several dozen variable stars the presence of an atypical type of star, bright blue and hot. Unlike most of the other stars in the observed cluster, which seemed to have a common past and thus to have formed at the same time, the stars discovered left him perplexed. Indeed, the stars in question had all the characteristics of a newly formed star, something that seemed more than unlikely within this globular cluster, whose age is estimated at over 11 billion years. However, these blue stars, which defy the rule of the Hertzsprung-Russell diagram, do exist. This diagram, used to study stellar populations, is in fact a graph showing the luminosity of a set of stars as a function of their effective temperature. But Alan Sandage's recently discovered star type is an exception to the rule, as it doesn't fit neatly into this spectral classification. Indeed, a blue straggler, which is a massive main sequence star, should theoretically not exist in this globular cluster. The scientific community therefore set out to elucidate what it considered to be the equivalent of an anomaly. When and how did such a massive star, 2 to 3 times the mass of the other main sequence stars in its host globular cluster, come into being? As more and more similar stars came to light, several theories began to emerge. The most obvious of these was that the existence of such a star was potentially linked to its period of formation. The latter must have been much more recent than the formation of the cluster population as a whole. However, this explanation failed to convince most astronomers. In fact, these late-forming stars needed large quantities of dust and gas to form. However, the cluster got rid of these residual elements a long time ago, during its formation. The second hypothesis was that this star must be foreign to the cluster in which it was detected. Although spotted in the field of observation of the cluster under study, it might be physically unrelated to it and located on a different plane. In the same vein, another idea has also been put forward. The star may have been torn from the galaxy's disk and captured by the star cluster when it was a little too close to it. These last two theories were not accepted for very long, not least because of the location of these atypical stars within their host globular cluster. Indeed, blue stragglers are essentially located in the most central regions of the stellar cluster that hosts them, implying that their physical integration into the structure has not occurred recently. This possibility is inconsistent with their recent formation. A final theory, dating back to 1964, was based on possible interactions within the existing group of stars. Astronomers Fred Hoyle and W.H. McCrae put forward an identical hypothesis, namely that 2 neighboring stellar mass stars, forming a tight binary system, would have collided or transformed matter and eventually merged, giving rise to this massive, luminous colossus. For several decades, the mystery remained unsolved. Intrigued, many astronomers have continued to study these most massive and ancient groupings of stars in the universe, in search of answers about the formation and evolution of the Milky Way, and indeed of the universe. The 47 Tucanae cluster, one of the largest in our galaxy, is one of the most closely observed star clusters. Located in the Tucanae constellation, around 15,000 light-years from Earth, it is a relatively compact globular cluster, with an estimated diameter of 140 light-years. In 1991, aided by the Hubble Space Telescope, itself equipped with a high spatial resolution, ultraviolet-sensitive camera, a team of astronomers discovered the presence of several blue stragglers at the heart of the cluster. In their statement, the scientists revealed that they had resolved 21 of them, which they believed to be extraordinarily concentrated in the center. Their location seems to support the hypothesis that these stars are created by collisions, mergers, or close encounters between stars. The fact that they are located within the cluster itself, in its densest and most luminous part, also explains why these massive stars have remained invisible for so long. Indeed, only instruments employing high spatial resolution, coupled with ultraviolet sensitivity, are able to study the compact core of 47 Tucanae and many other groups of stars in greater detail. The use of this new technology has thus opened the door to abundant discoveries. Whereas ground-based images yielded only a few dozen stars in a precise area of the cluster studied, this onboard camera will have enabled the resolution of around 600 stars. Comparing the images obtained by these two techniques enabled astronomers to discover 21 stars that are extraordinarily bright in ultraviolet light. By comparing the luminosity and temperature of these particularly bright stars with a computer model predicting how main sequence stars appear in ultraviolet wavelengths, the scientists concluded that they were indeed blue stragglers. What's more, the high concentration of these specific stars towards the cluster's core suggests that they are relatively much more massive than the vast majority of its component stars. The high mass of some of these stars could also be explained by the presence of binary systems. A considerable population of millisecond pulsars and binary stars has also been discovered in 47 Tucanae, supporting the idea that close gravitational encounters between single stars, binary stars, and even binary systems could well take place in this zone. A few years later, in 1995, another group of astronomers focused on one of these blue stragglers. Still using the Hubble telescope, they were able to observe its behavior. The result, which they describe as exciting, will help to support a number of existing theories on the formation and evolution of these enigmatic stars. After analyzing the star's spectrum and measuring its temperature, radius, and rotation speed, they were able to obtain the star's mass. While its derived temperature and mass are consistent with the specifics of a normal star, with a mass around 1.7 times that of the Sun, its speed is unexpected. In fact, it turns out that this blue star rotates 2 to 3 times faster than its counterparts, and 75 times faster than our Sun. All these elements offer scientists the opportunity to understand how blue stragglers are formed. While it is becoming clear that a star of this type is created by the fusion of two low-mass stars, it remains to be seen by what process. Was it a violent collision, or a long process of fusion between binary stars, with one siphoning energy from the other? According to the scientists, this second hypothesis produces rapid orbital movements of the binary star, generating, in effect, an accelerated rotation of the pair in the final phase of fusion. Over the years, thanks to cutting-edge technology, more and more blue stragglers have been detected. In a 2006 study, which examined the chemical signatures of 43 of the blue stragglers in Cluster 47 Tucanae, 6 of them had lower concentrations of carbon and oxygen than their counterparts. The scientists concluded that their surface material must almost certainly have been literally sucked up from the deep interior of a parent star in a double system. The same researchers also studied these atypical stars in 56 other globular clusters. They found that the amount of blue stragglers in a particular cluster was unrelated to the potential collision rate. Thus, they partly put to rest the theory that these stars were the result of collisions between several stars. Instead, there did seem to be a correlation between blue stragglers and the rate of binary stars in these different globular clusters. This finding enabled them to prove that the majority of blue stragglers, including those closest to the core of these clusters, are indeed the descendants of two binary stars. It took more than 50 years for astronomers to unravel the mystery of these immature-looking yet ancient stars. Among the many stars studied in an attempt to better understand these curious objects, one has caught astronomers' attention for its strange behavior. This is the star SS Leporis, also known as 17 Leporis. Long catalogued as a variable star in the Hare constellation, SS Leporis is in fact a rather unusual binary star system. The two stars revolve around each other in 260 days, and the distance between them is only slightly greater than that between the Earth and the Sun. The largest and coldest of the two stars, a red giant, spans a quarter of this distance. To give you an idea of their proximity, the orbit with its companion could be compared to that of Mercury with the Sun. But above all, this red giant, which is in fact the more evolved of the two, paradoxically happens to be the less massive of the two stars. How could these mass ratios be reversed in such a way? To unravel the mystery of this unusual phenomenon, scientists decided to study the dynamics of the system while observing the most central parts, inaccessible with conventional telescopes. In 2010, astronomers created a virtual telescope 130 meters in diameter, offering a view 50 times sharper than that provided by NASA's Hubble Space Telescope. To achieve this, they combined light captured by 4 telescopes at the European Southern Observatory's Piranal Observatory. While the scientists were convinced that matter was transiting from one star to another in this unusual system, they didn't know how. Their discovery has enabled them to assert that this mass transfer does not follow similar patterns already known. The new, extremely precise observations showed that the red giant is smaller than they had previously thought. Its companion, a blue star, although smaller in size, turns out to be the hotter of the two. Its mass is around 2.7 times that of the Sun, compared with 1.3 times for the red giant. The process by which this star flows matter onto its companion star proves far less easy to explain, especially as no flow of matter is visualized between the two stars. Researchers are beginning to put forward the idea that the blue star, with its highly superior mass, has been vampirizing its imposing neighbor for almost 500,000 years. The notion of a vampire star which feasts long and insidiously on a neighboring star became obvious. The vampire star seems to be sucking not the blood, but the hydrogen and plasma from its neighbor, who thus becomes a victim with a shortened lifespan. Unlike cannibal stars, vampire stars, better known under the scientific term of symbiotic binaries, do not quickly devour their prey. The first cannibal star was studied by the European Space Agency in 2004. Researchers had the opportunity to observe a fast-rotating star. It is a super-dense neutron star just 20 kilometers across, initially 8 times more massive than our Sun. Although its mass is astronomical, a thimble's worth of its material, weighing close to 1 billion tons, its small size has meant that it has been virtually invisible to observational instruments. However, on December 2, 2004, it emitted a sudden and powerful X-ray eruption, revealing itself to Integral, the European Space Agency's International Gamma Ray Astrophysics Laboratory, and NASA's Rossi X-ray Timing Explorer spacecraft. The measurements confirmed that this was one of the fastest spinning pulsars ever studied, with a dizzying speed of 600 rotations per second, which is gradually accelerating. This frenetic rotation is the result of the absorption of gas extracted from a companion star. When this gas crashes onto the star's surface, it causes it to heat up to a temperature of almost 1 billion degrees, releasing extraordinary quantities of X-rays and gamma rays. In short, it makes short work of its neighboring star, which shrinks irreplaceably. This is why this cannibal star is nicknamed the Black Widow. Even more unusual, in 2015, a NASA telescope caught a cannibal star in the middle of a feast. This is a white dwarf at the end of its life, whose gravity is so powerful that it is capable of attracting and eventually disintegrating a nearby telluric planet. In 2011, still intrigued by this unexplained phenomenon, scientists also turned their attention to the open cluster NGC 188. Located in the Cepheus constellation, 6,680 light-years from our solar system, this cluster features 21 blue stragglers, most of whose stars are over 7 billion years old. Detailed observational data from the WIYN telescope at the Kitt Peak Observatory in Tucson, Arizona, were used to analyze and compare the 3 main theories concerning the formation of blue stragglers: star collisions, star mergers, or mass transfer from one star to another. Collisions or mergers would be conceivable if the companion stars appeared more massive, which is not the case. The mass of these companions, whose luminosity remains low, can only be determined by observing the blue stragglers. These are subject to a gravitational force from the red giants, creating an oscillation during their orbit. By observing the movements of the blue stragglers, they were able to determine that 16 of them must have a much more discrete companion. The data collected enabled the researchers to assert that each companion star had a mass about half that of the Sun, corresponding to a white dwarf. But what better way to confirm their assertions than with an image? However, in 2011, the technical means available are not yet sufficient to observe this type of star, whose luminosity is relatively low, especially as it lies close to a sparkling blue straggler. Using ultraviolet wavelengths, a team in 2015 was able to prove that 7 of the 21 blue stragglers had a white dwarf as a companion, thus supporting the 2011 conclusions of their colleagues. In her study, she points out that only white dwarfs formed within the last 250 million years can be detected, the others being too cool to be detected and thus confirmed. Among the other blue stragglers, 7 showed evidence of mass transfer between stars by other means. All in all, it proves that a quarter of the oldest stars do not evolve into red giants, but turn into blue stragglers with surprising luminosity and strange behavior. We now know how blue stragglers are formed. Stars that appear bright and fresh alongside many faded stars in ancient clusters. They give themselves a new lease on life by absorbing matter from their companion stars. These are not stars that have migrated or collided, giving rise to a massive bright new star. It's a case of one star vampirizing another, giving itself a second life. Vampire stars are mainly observed in stellar clusters. These groups of stars, which formed more or less at the same time as their host galaxy, are home to the oldest stars. Almost exclusively populated by red giants, they nevertheless shine brightly in our starry skies due to their high concentration. Millions of stars are crammed into an area that in other parts of the galaxy might contain only one star or even none at all. In these spherical clusters, some stars appear far less advanced than the majority. But if these younger-looking stars were the result of collisions and mergers, they would have to show age differences. However, the study of these blue stragglers within the same cluster has shown that they all formed at roughly the same time. They are therefore not the result of collisions due to random displacements. Since 2011, scientists have known that they are the result of mass transfer between 2 very specific stars. Let's take a closer look at the process by which these stars manage to rejuvenate themselves. When 2 stars form a binary system, orbiting each other, they evolve according to the same pattern. As the 2 stars age, they gradually evolve into red giants. In the process, their volume increases steadily, until they reach several hundred times their initial size. As they move ever closer together, the distance between them shrinks considerably. Gravitational interactions become increasingly important. Inevitably, the star with the highest mass outweighs its companion star. As its gravitational force is greater, it will gradually absorb the outermost layers of gas, which are only weakly held back by the gravity of the second star at the end of its life. Mass is inexorably transferred from the cooling red star to the star that is gradually regaining its youth. By stirring up the hydrogen fuel, the latter generates nuclear fusion at a faster rate. The hydrogen burns hotter and bluer. The least massive, which ends up completely stripped, retains only its core. It loses its red giant status and becomes an insignificant white dwarf. Meanwhile, the vampire star gains extraordinary mass, and after its rejuvenation, begins to shine brightly. At first glance, she may appear youthful, but her real age is much more advanced, just like those who undergo facelifts. While the mystery surrounding the formation of vampire stars seems to have been solved, studies of them are still going strong. The stars contained in the clusters of each galaxy have yet to reveal all their secrets. All the more so, as these stars are the ancient witnesses of many cosmic formations. But we still have to get them to talk. Eager to learn more about their past, Canadian students from the Department of Physics and Astronomy at the University of British Columbia published a study in 2016. It focused on the formation and evolution of blue stragglers in the 47 Tucanae cluster. Knowing that all the stars in the same cluster are at the same distance from the observation site, i.e. the Earth, it becomes easier to compare their apparent magnitude. The students created a color magnitude diagram, which is simply the observational version of the Hertzsprung-Russell diagram. They were able to observe the population of blue stragglers in this cluster. Their findings suggest that the existence of these stars, which are too blue in this aged environment, is the result of a number of mechanisms, as well as being dependent on the environment in which they evolve. They began by separating the stars into different populations. In equal numbers, bright blue stragglers and faint blue stragglers, main sequence stars, binary main sequence stars, and red giants. In a second step, the researchers estimated the cumulative distribution of each of these categories along the cluster radius of their diagram. They found that bright blue stragglers are more concentrated in the inner regions, while fainter blue stragglers are much more prevalent in the peripheral zone. What's more, the cumulative radial distribution of bright blue stragglers is not echoed by other populations, making it difficult to link their formation to a specific group of stars. On the other hand, faint blue stragglers and main sequence stars show a very similar distribution, suggesting that a binary system may indeed be at the origin of these atypical stars. In short, the study demonstrated that different mechanisms could lead to the formation of blue stragglers. Interactions between several systems seem to dominate in the central regions, resulting in more massive and luminous objects, while binary evolutions appear to be the most common scenario in the periphery of these clusters, generating fainter blue stragglers. They were also able to conclude that the evolution of blue stragglers at equal mass is similar to that of main sequence stars. While these findings still need to be confirmed by future observations, they nevertheless allow us to learn ever more about these strange and surprising blue stragglers. Again, thanks to the Hubble Space Telescope 26,000 light-years from our Sun, blue stragglers have been detected this time, not in a cluster, but in the bulge of the Milky Way, i.e., at the very heart of the galaxy. In this congested area, which corresponds to the former hub of our Milky Way, amid countless aging stars, blue stragglers also reside. In 2006, a 7-day survey was carried out. Called Sagittarius Window eclipsing extrasolar planet search, its aim was to detect hot Jupiter-like planets orbiting very close to their stars. After observing and collecting information on the variability of 180,000 stars in the extremely populated central bulge of our galaxy, the scientists were able to determine that most of them were aging sun-like stars and cooler red dwarfs. In an area once populated by giant blue stars that exploded as supernovas billions of years ago, however, some stars appeared to be out of the neighborhood. Scientists discovered 42 blue stars that were far too bright and hot for the other stars in the galactic bulge. As you might expect, these are probably blue stragglers. If the existence of such rare stars in this part of the galaxy was suspected, it has now been proven. Until now, this area could not be accurately observed, as younger stars along the line of sight to the bulge made visibility confusing. Of the 42 candidate blue stragglers, scientists believe that 18 to 37 could actually be vampire stars. These stars, although very luminous, are undoubtedly old ladies, between 10 and 11 billion years old. Having vampirized a few companion stars, they have given themselves a much longer lifespan than their fellow stars. As for the rest of the blue stars, they may be genuine young stars or objects outside the bulge. Although scientists believe they have understood how blue stragglers evolve in globular clusters, their observations are not yet complete. Indeed, if one thing is certain, it's that they can never be certain of having fully elucidated the workings of our universe. So vast and constantly evolving is it. Above all, the advent of new, ever more advanced technologies means that discoveries can be made that sometimes drastically call into question past deductions. This is why so many star clusters are constantly in the sights of numerous telescopes. A case in point is the Messier 30 cluster, located in the constellation of Capricorn, some 28,000 light-years from our solar system. Discovered in 1764 by French astronomer Charles Messier, it was initially thought to be a round nebula containing no stars. However, 20 years later, this formation, whose diameter is around 90 light-years, took on the status of a cluster with an indefinable core due to its very high concentration and density of stars. Its spectral study, which classifies it as F3, indicates that it is extremely poor in heavy elements. It is therefore a very old globular cluster in our galaxy, probably 13 billion years old. For astrophysicists, this swarm of several 100,000 stars represents a case study that will certainly enable them to learn even more about the evolution of stars. With the help of the Hubble Space Telescope, astronomers have identified two distinct types of straggler star, just as their colleagues had previously done when studying the 47 Tucanae cluster. In a study published in 2009 by Francisco Ferraro, an astronomer from the University of Bologna in Italy, the hypothesis that blue stragglers can evolve in this way as a result of different processes seems to be confirmed. These stars, which are not as young as they first appear, are indeed the result of stellar encounters. Although their mass is greater than the typical mass of individual stars in Messier 30, they do not all have the same properties, which means that the two formation scenarios already presented are equally valid, but also that they can occur simultaneously in the same cluster. Potential collisions thus lead to the fusion of several stars, which, forced to mix their fuel, fan the flames of nuclear fusion. And as we observed earlier, the evolution of binary systems can just as easily spawn a blue straggler alongside a longtime companion, then devoured on the surface. What's more, by compiling the data collected by the Wide-Field Planetary Camera aboard the Hubble Space Telescope, the astronomers found that blue stragglers, although widely scattered within the cluster, are particularly more concentrated near its center than the so-called medium stars that populate it for the most part. They deduced that these blue stragglers are more massive than most of the stars in this structure. Indeed, as Francisco Ferraro explains, more massive stars tend to sink deep into the cluster like a billiard ball sinking into a honeypot. Whatever the process used to bring these stars back to life, they all have one thing in common. Their mass is around twice that of the typical mass of the individual stars in the cluster. To explain this unquestionable concentration in the central region of Messier 30, where interactions between stars are almost inescapable, astrophysicists have developed a hypothesis. They assume that the Messier 30 cluster underwent a major core collapse 1 or 2 billion years ago. During this cataclysmic event, a large number of stars would have been thrown towards the center of the structure, inevitably leading to a rapid increase in their density. As a result, the first family of blue stragglers would have emerged. As a result of these reorganizations, the twin systems would also have been greatly disturbed, inevitably accentuating the vampirism mechanism to which they are highly prone, giving rise to a second line of blue stragglers. In short, the two existing populations of stragglers that populate Messier 30 are the stigmata of the cluster's core collapse, probably 2 billion years ago. For some, this discovery is direct evidence of the impact of star cluster dynamics on stellar evolution. It now remains to be seen whether other globular clusters also possess this diverse population of blue stragglers. The hunt was on for blue stragglers, and consequently for vampire stars. In the years that followed, many researchers set about the task of detecting as many of these stars as possible, also known as cataclysmic variables. In a 2021 publication, Vikrant Jadhav and Annapurni Subramanian report on their meticulous census carried out thanks to the Gaia telescope. Launched in 2013 by the European Space Agency, the Gaia telescope offers excellent positional accuracy, making it possible not only to detect blue stragglers in open clusters, but above all, to study them like never before. Studies are now focusing more on open clusters because of the better distinction they offer between stars, as there are fewer of them in the same area, and consequently, they are closer together. The researchers were thus able to study 670 clusters, all over 300 million years old. They were able to identify 868 blue stragglers in 228 distinct clusters. These are mainly found in the most massive and oldest star clusters. They also confirmed that they are mainly located near the center of these same clusters, and all more massive than the extinct stars of the main frequency. Finally, they were able to draw up a detailed inventory of these exotic stars, and even deduce their formation mechanism. According to their study, it turns out that over 54% of blue stragglers are vampire stars that formed by mass transfer, feeding long but surely on their close companion star. 30% of these rejuvenated stars have benefited from a collision with a second star. Finally, 10 to 16% of blue stragglers came into being as a result of interactions between more than two stars. Thanks to this study, we now know a little more about stellar systems. Numerous observations of these blue stragglers are still in progress, notably using ultraviolet imaging integrated into the AstroSat telescope, the first dedicated space observatory, and the Devasthal optical telescope at Nainital, both in India. Nevertheless, globular clusters are not being neglected. Quite the contrary, in fact. One of them, the famous Hercules globular cluster, Messier 13, 25,100 light-years away, is one of the most beautiful objects to observe through a telescope from the Northern Hemisphere. It, too, contains numerous blue stragglers. The Galactic globular cluster NGC 6256, located in the constellation Scorpius, some 27,400 light-years from our solar system, has also benefited from close observation. In a study published in 2022, scientists reported that it hosts a double sequence of blue straggling stars. Like the Messier 30 cluster, a detailed photometric study of its bulge concluded that it is at a very advanced stage of dynamical evolution, as evidenced by its central segregation of blue stragglers from lighter stars. On the other hand, while Messier 30 reached this stage of evolution around 2 billion years ago, the process in the cluster, located in the Scorpio constellation, seems less ancient. Comparison with collisional models suggests that a short-lived event probably occurred 1 billion years ago, favoring the formation of a population of blue stragglers as a result of collisions. These represent almost 60% of the total population of the observed cluster. However, examination of the positions of the two brightest blue stragglers indicates that the cluster may have undergone an even more recent recollapse, as recently as 1 million years ago. While the vast majority of their fellow stars bear the scars of nearly 12 billion years of existence, these stars give the impression of having recently returned to their adolescence. But this hypothesis will require further study before it proves to be correct. These extremely youthful stars may, after all, be the result of collisions generated by evolving red stars. However, this explanation, though possible, remains weak in the eyes of the specialists. While observing the blue stragglers across various clusters, a group of astronomers led by Professor Ferraro of the Department of Physics and Astronomy at the University of Bologna noticed another peculiarity. They found that some of these puzzling objects form by mass transfer in binary systems, triple systems, and sometimes by stellar collisions, and thus having different structural characteristics, preferred certain environments to others. Their discovery, published in May 2023 in Nature Communications, is conclusive. Young blue stragglers prefer calm environments. The scientists were interested in blue stars with rotational speeds in excess of 40 kilometers per second, or 25 miles per second. Of the clusters studied, all of which are very old, 4 have a low density. These are Messier 4, Omega Centauri, Messier 55, and NGC 3201. The 4 other clusters selected for this observation, which are in contrast very compact high-density clusters, are 47 Tucanae, Messier 30, NGC 6397, and NGC 6752. These groupings of stars, with their different structural characteristics, provide a fantastic laboratory for analyzing the behavior of 320 blue stragglers in 2 contrasting environments. These newly formed stars, either through stellar collision or vampirism, start spinning very fast at the beginning of their rebirth, transforming themselves into veritable cosmic spinning tops. But inevitably, this speed gradually decreases. This is why rotation speed is an essential diagnostic tool for distinguishing newly created blue stragglers from older ones, which inevitably exhibit slower rotation. Following their observations and a survey of the fastest rotating vampire stars, the scientists concluded that fast-rotating blue stragglers are more likely to be found in low-density clusters. In fact, 40% of blue stragglers observed in low-density clusters rotate at high speeds, compared with just 3 to 4% in high-density clusters. So researchers who had previously expected to make the opposite discovery, thinking they'd find more fast-spinning blue stragglers in high-density clusters, were extremely surprised by their findings. It opens up a new avenue of exploration for them to try and understand the dynamic processes that characterize the evolution of these vampire stars in different environments. This discovery is likely to have a profound impact on their understanding of the evolution of star clusters, as well as on the consequences of binary systems and stellar collisions. In the course of their observations, scientists are sometimes surprised to discover rare phenomena they may have suspected existed, but had never before had the opportunity to see with their own eyes. For example, they witnessed a super explosion at the heart of a vampire star system. The super explosion was detected in 2019, when they carried out yet another search of the countless archives of NASA's Kepler spacecraft. Kepler was designed to find exoplanets by searching for stars that gradually darken as a planet passes through their bright firmament. This technique is therefore ideal for detecting other transient astronomical phenomena, i.e., objects that experience fluctuations in their luminosity. This is how they discovered that Kepler's archives contain some rather unusual data, showing a super explosion within an unusual binary system. This system consists of a white dwarf star and a brown dwarf, orbiting its companion star every 83 minutes, just 400,000 kilometers apart, roughly the distance between the Earth and the Moon. Because of this close proximity, the white dwarf's intense gravity sucks matter from the brown dwarf. This torn-off material gradually feeds the accretion disk, which spirals toward the heart of the white dwarf. As luck would have it, Kepler was observing in the direction of this system when a very intense phenomenon occurred. He was able to record a super flare coming from this binary system. It brightened by a factor of 1,600 in less than a day, before slowly fading away and then dying out. But that's not all. With Kepler collecting data every 30 minutes, every detail of this massive explosion could be studied. While theories suggest that such an increase in brightness is sudden, the phenomenon in question proved the opposite. In fact, a slow increase in luminosity was observed before the explosion actually took place. Why this slow start? It remains a mystery to this day. According to current theories, this super explosion could take place when the accretion disk reaches a tipping point. As it accumulates matter, it also gradually increases in size. When its outer rim comes into gravitational resonance with the brown dwarf, this would lead to thermal instability. The disk would then overheat, triggering the super explosion. This theory makes perfect sense when we compare the temperature of the accretion disk at the different stages immortalized by Kepler. The accretion disk, whose usual temperature is barely 5,000 degrees Celsius or 9,000 degrees Fahrenheit, would have reached 11,700 degrees Celsius or 21,000 degrees Fahrenheit at the height of the super explosion. It remains to be seen whether Kepler's archives contain any other events of this type, however rare, that would support this hypothesis. As you can see, nature never ceases to surprise us, each time revealing only a tiny part of its mysteries. Among the many other astonishing discoveries, one of them concerns the HR 6819 system. In 2020, a team of astronomers from the European Southern Observatory thought they had discovered the nearest black hole to our Milky Way, accompanied by a star in this system. Shortly after publication, however, colleagues from an international team based at Belgium's Dutch-speaking University of Leuven challenged this original study. According to them, this system does not contain a black hole, but is a two-vampire star system in a transitional stage, extremely rare to observe, although not marginal on the scale of the universe. To unravel this mystery, the two teams agreed to join forces. After agreeing that there were indeed two sources of light in this system, they turned their attention to how far apart they were. Are they two stars orbiting each other in a confined space, or two stars relatively far apart? Thanks to data collected by the Gravity and Multi-Unit Spectroscopic Explorer instruments on the European Southern Observatory's Very Large Telescope Interferometer, they were able to confirm that these two light sources are very close together, only a third of the distance separating the Earth from the Sun. What's more, they believe they witnessed the immediate consequences of a vampire star attack. Indeed, as one of the two stars was stripped by its companion, the latter began to spin much faster than before. The astronomers, lucky enough to have been able to capture this brief post-interaction phase, intend to take a closer look at this vampirism in action. Perhaps they will finally be able to understand how this phenomenon affects the evolution of massive stars, and de facto, the formation of their associated events, such as gravitational waves and violent supernova explosions. And as a result, another mystery remains to be solved. Where does the black hole closest to our Earth hide? To date, astronomers have counted over 1,000 cataclysmic variables. The two stars in this type of system are inevitably close to each other, so that the white dwarf is able to suck matter out of its donor star. But only a dozen of these duos have orbital periods of less than 75 minutes. In 2022, Kevin Burge of MIT's physics department published in the journal Nature that he had spotted one of these cataclysmic variables 3,000 light-years away, in the direction of the constellation Hercules. The two stars in question are so close together that the orbit, which takes just 51 minutes to cover, is the shortest ever observed for a cataclysmic variable. This duo, named ZTFJ 1813 plus 4251, is therefore after a very long life of nearly 8 billion years in full transition. The white dwarf, whose diameter is around 1.5 times that of the Earth, and whose mass is approximately 56% more massive than the Sun, looks rather strange compared to its companion, which is a star similar to our Sun on the verge of becoming a red giant. Above all, scientists have discovered that the vampire star has finished absorbing its neighbor's hydrogen and is beginning to strip it of its helium. This infernal duo is therefore in the process of switching from hydrogen accretion to helium accretion. While they were aware of the existence of cataclysmic hydrogen and cataclysmic helium variable populations, the process by which these stars switch from one to the other was not yet known. Their simulations predict that in approximately 70 million years, the two stars will be so close that their orbital period will be reduced to 18 minutes. The duo will then become a cataclysmic helium variable. They have thus clearly identified the missing link in astrophysics that could explain this transition. When the two stars are close to each other, the inevitable will happen. They will merge and explode, putting an end to the emission of gravitational waves. After this nova, will calm return to this part of the cosmos? And if so, for how long? Unless a black hole appears. During this sudden event, in which both stars are subjected to incredible convulsions, the outer parts of the hydrogen layer and many fragments of the molten products are literally ejected into interstellar space. Depending on the mass and composition of the two stars forming this pair, their evolution may differ. Cataclysmic variables are classified into several distinct groups, often named after the archetype of a bright star with the same characteristics. These include Geminorum variable stars, magnetic or polar cataclysmic variable stars, intermediate polar variable stars, AM Canem, Venaticorum variable stars, and SW Sextantis variable stars. The former, also known as dwarf novae, undergo large explosions caused by deformations of the accretion disk when their rotation enters resonance with the orbital period of the companion star. As for magnetic systems, most of them feature strong variable polarization. Intermediate polars show a partially destroyed accretion disk, while polars prevent the formation of an accretion disk. For the moment, however, the most spectacular phenomenon ever studied is that which causes the vampire star to self-destruct during a supernova. When the accretion process lasts long enough, it leads the white dwarf, the vampire star, to reach the Chandrasekhar limit. The Chandrasekhar mass corresponds to the maximum electron degeneracy pressure an object can withstand, without undergoing gravitational collapse. To the extent that the white dwarf exceeds this limit, the increasing internal density causes the carbon to melt abruptly. This leads to a Type 1a or thermonuclear supernova explosion, which is fatal. The vampire star, having been too greedy, undergoes a cataclysmic explosion, leading to its disintegration. After shining like no other of its many neighbors, it disappears forever from the cosmos, leaving only the remnants of its explosive end of life. The interaction of the antenna galaxies in the night sky is a veritable firework display, illuminating thousands of nebulae and young star clusters. It's a spectacle of unspeakable beauty. the arms of the galaxies were deformed and the cores brought close together. The impact sent out two immense jets of stars and gas, earning this celestial duo the nickname the Antennae. With a 100mm aperture, it's possible to observe the galaxy duo, which appears as a diffuse spot with no detail. When viewed through a 200mm telescope, the dual nature of the object becomes clear. Its shape takes on the appearance of a V elongated towards the west. But it's only when you use 300 to 400mm instruments that the spectacle becomes striking. The two Antennae galaxies form a magnificent, asymmetrical boomerang. NGC 4038 to the north represents the brighter, more curved part, while NGC 4039 to the south is thinner. Astronomers believe that within 400 million years these two galaxies will have merged. For us, this gigantic timescale is nothing compared to the lifetimes of these stars. This collision could give rise to a larger galaxy, perhaps of the elliptical type. The nearest ultra-bright infrared galaxy is ARP 220. It is located around 245 million light-years from the Milky Way, in the constellation of Serpent. ARP 220 is the result of the collision of two galaxies that are currently merging into one. ARP 220 radiates mainly in the infrared. Most of its luminosity comes from the intensive formation of young stars, since it is a star-forming galaxy. Scientists have observed over 200 stellar clusters at the heart of this galaxy, some reaching masses of the order of 10 million solar masses. ARP 220 has an active galaxy core. This core is characterized by a compact region at the heart of the galaxy. Its luminosity is higher than average and not of stellar origin. In theory, it results from accretion by a supermassive black hole. The Whale constellation is the fourth largest constellation in the sky. Its best-known stars are Mira and Difta. Within this constellation lies the ARP 147 system, also known as the Ring Train. This pair of colliding galaxies lies 440 million light-years from Earth. The Ring Train perfectly represents the most spectacular effects of galaxy collisions. The two galaxies making up the pair are considered special galaxies in that they are neither elliptical, spiral, barred spiral, nor lenticular. They are, however, regular in shape. The two galaxies are shown, one in profile, evoking the number 1, and the other from the front, appearing to represent the number 0. Together they form a gigantic 10. This extraordinary figure in the sky is the result of an extremely violent collision. The galaxy on the left, representing the number 1, has smashed right through the galaxy on the right, representing the number 0. In the same way that a pebble emits a wave when it comes into contact with water, the collision created a wave at the point of impact. This density wave traveled outwards through the affected galaxy, colliding with the star's gas and dust as they tumbled towards the center, under the effect of an increased gravitational force. As a result of the collision, the high-temperature matter clumped together, stimulating the formation of young stars. A red spot can be seen at the bottom of the right-hand galaxy forming 0. This is probably the remnant of the galaxy's nucleus after the collision. Made up of around 50 individuals, the local group is a very modest cluster in which our galaxy, the Milky Way, lies. Nevertheless, its evolution has been as tumultuous as that of larger galaxy groupings. Based on the stigmata found on the Andromeda galaxy, also known as M31, numerical simulations have attempted to reconstruct its past. At present, M31 is the only galaxy in the local group larger than the Milky Way. 5 billion years after the Big Bang, the local group is made up, in addition to the future Milky Way, of two rather large galaxies, one of which is 4 times more massive than the other. Their relative proximity generates a mutual attraction that brings them closer together, until they inevitably collide 4 billion years later. The merging of these two galaxies gives rise to the Andromeda Galaxy. The distances between the stars of the two galaxies are so great that another head-on collision is ruled out. Tidal forces create a gigantic trail of stars. Part of it returns towards the larger galaxy, the result of the ongoing merger, while the other part escapes the latter's grasp and gathers into two dwarf galaxies known as the Magellanic Clouds. Their speed is such that they soon find themselves close to the Milky Way. Supernovas are spectacular events marking the end of the evolution of a massive star. During these gigantic explosions, the energy released in a few seconds is comparable to that emitted by a star throughout its lifetime. The phenomena triggering these explosions vary, according to whether the star belongs to a binary system or to a single star. In the latter case, a supernova explosion will only occur if the binary system's companion star is a white dwarf. Under certain conditions, the white dwarf is gravitationally bound to its companion star, absorbing matter from the latter's surface layers. The captured material falls onto the white dwarf and heats up. When it exceeds the mass limit at which a nova is formed, nuclear reactions are set in motion until it is destroyed. In the case of an isolated star, the star itself explodes once all internal nuclear fusion cycles have taken place. Gravity then takes over, and the star contracts very rapidly. The resulting heating triggers uncontrolled nuclear reactions in the core. An explosion occurs, releasing enough energy to destroy the star. The explosion leaves behind a trace called supernova remnant. This is an expanding cloud of gas. Astronomers identify supernovas by their characteristic light curve. They exhibit a rapid increase in luminosity that lasts several days. When this luminosity reaches a maximum, it stabilizes for around 10 days. It then decreases discontinuously, followed by a steady decline. Interpretation of the light curve enables us to study the evolution and dynamics of the explosion. Because of their extreme brilliance, supernovae are one of the favorite objects of astronomy enthusiasts. And it's thanks to them that around 50 supernovas have been discovered every year since 1990. Several supernovas have left their mark on the history of astronomy. On February 24, 1987, Canadian-born astronomer Ian Shelton set out to take long-pause photographs of the Large Magellanic Cloud, a dwarf galaxy close to the Milky Way, visible from the southern hemisphere. While developing his photographs, he was surprised by the presence of a new star. After consulting several colleagues, he discovered that the star had also been seen by others. The first traces of the explosion to reach Earth were carried by neutrinos, which are difficult to detect particles emitted rapidly, in very large numbers, shortly before the star's increase in luminosity. SN 1987A was the first supernova explosion of the 20th century to be observed by the naked eye under optimal observing conditions. It provided crucial data for understanding the mechanisms of these stellar explosions. The general principles governing the supernova phenomenon have been confirmed. Studies clearly show that 99% of the energy emitted by supernovas is in the form of neutrinos. But for the first time in 1987, thanks to the supernova explosion, neutrino emission was observed instantaneously. When the star's core collapses under the effect of gravitation, electrons merge with protons to form neutrons and neutrinos. The latter interact very little with matter and are immediately released. Another feature of SN 1987A is that the star that gave rise to it was a blue supergiant. The presence of 3 gas rings around the supernova made it possible to understand that the star had evolved from a red supergiant to a blue supergiant around 20,000 years before the explosion. This progenitor star is called SK 69202, or Sandelic 69 degrees 202a. It was born 10 million years ago with a mass 20 times that of the Sun. Astronomers were surprised that it was a blue supergiant rather than a red one, as it was suggested at the time that only stars in the red supergiant stage evolved into supernovas. Today, the supernova afterglow remains the focus of numerous observations, even if the search for the compact residue has so far been unsuccessful. Thanks to numerous instruments on the ground and in space, the supernova has been observed continuously, both in terms of electromagnetic radiation and by neutrino detectors. The phenomenon occurred at a distance of around 51.4 kiloparsecs from our planet. In May 1987, it reached its maximum brightness with an apparent magnitude of around +3. Supernova 1993J occurred in galaxy M81 in 1993. It was discovered by a Japanese amateur astronomer and was one of the brightest supernovas of the 20th century. Its ancestor has been identified as a K-type supergiant star, characterized by an excess of ultraviolet light, which may be due to the surrounding hot stars or a hot binary companion. SN 1572, also known as Tycho's supernova, is a supernova in the constellation Cassiopeia, 7,500 light-years from Earth. It owes its name to the Danish astronomer Tycho Brahe, who first observed it on November 11, 1572. On that day, it appeared much brighter than Venus, with an apparent magnitude of -4. It wasn't until March 1574 that its brightness dropped below the threshold of visibility to the naked eye. This supernova became one of the most famous events in the history of astronomy, since it contradicted the Aristotelian theory of the inalterability of the cosmic world. Indeed, since ancient times, the world beyond the moon had been considered unshakable. For scientists of the time, it was only between the Earth and the Moon that new celestial objects could appear. Tycho Brahe's discovery implied a new object much further away. Over the course of months of observation, he also discovered that the object had not changed position relative to the fixed stars, and could therefore not be a planet, but another star. In 1573, Tycho Brahe published his discovery, calling it a new star. This revolutionary expression turned astronomy on its head. It led to the development of better astronomical classification catalogs and improved observational instruments. The supernova's progenitor star was probably a dwarf that had drawn in matter from another companion star until it exploded. Type 1 supernovas, like SN 1572, do not involve the formation of extraordinary nebulae. That's why its faint afterglow was only discovered in the 1960s. Thanks to the Chandra Space Telescope, astronomers were provided with astonishing images of Tycho's supernova. These showed lumps in the remains of the star, as if several ignition points had existed within the supernova. The explanation is that SN 1572 underwent an asymmetric explosion. The explosion produced a large cloud of expanding debris. A thin blue line, representing ultra-high energy electrons, can be seen around the perimeter. The dust formed is ejected into the cosmos. Numerous other stars adorn the supernova's vicinity, like sparkling white diamonds. SN 1604, also known as the Kepler supernova, occurred in the Milky Way in the constellation of Ophiuchus in 1604. It is a type 1a supernova, or thermonuclear supernova, resulting from the explosion of a white dwarf. In most cases, the latter captures the matter of a companion star until it reaches critical mass and explodes. In the case of Kepler's supernova, however, it appears to have been triggered by the merging of two white dwarfs. As there are no bright stars in the vicinity of the central region of the supernova's remnants. SN 1604 was observed by German astronomer Johann Kepler and was visible to the naked eye for over a year. Kepler was not the discoverer of the supernova, but it was he who carried out the most detailed research on the star. He wrote about it in his book, Sur la nouvelle étoile dans la pied de Ophiuchus, On the New Star in the Foot of Ophiuchus. This supernova lies at a distance of 20,000 light-years from our planet Earth. Its relatively low position on the horizon and declination of -21 degrees could have made it difficult to detect, but certain circumstances were favorable to its discovery. SN 1604 lies in a region where the planets of the solar system circulate. In October of that year, Jupiter, Mars, and Saturn were located in this very zone. What's more, with the Sun at the same time located around 60 degrees west of this region, the sky was easily observable in the early hours of the night. What's more, Tycho Brahe's discovery some 30 years earlier had sparked a great deal of interest among astronomers in observing the night sky. Today, NASA astronomers report that some debris from the explosion is still moving through space at speeds of up to 37 million kilometers per hour. The average speed of the clusters studied is around 16 million kilometers per hour. The four fastest clusters in SN 1604 are all heading in the same direction and have a similar chemical composition. This may mean that the debris is coming from a single layer of the progenitor star. These velocities have already been observed in supernovae and other galaxies, but only just after their explosion. In the case of SN 1604, the displacement of its remnants continues unabated, even 400 years later. Astronomers have yet to explain this phenomenon, but several theories have been suggested. The explosion could have been so violent that the material was ejected at very high speed, or the white dwarf's environment is lumpy, and the debris made its way along low-density paths without being slowed down. SN 1054, also known as a supernova of the year 1054, is famous for the afterglow it left behind after the explosion, known as the Crab Nebula. It is one of the most studied objects in the sky. The supernova was observed in 1054 and documented by Chinese and Arab astronomers. Numerous written sources attest to the explosion of a star in 1054. At the time, in China, transient stars such as comets, novas, or supernova explosions were called guest stars. Several accounts in official archives of events during certain dynasties relate this phenomenon in 1054. 3 other Japanese texts, individual chronicles, also mention this guest star at the same time. In the Arab world at the time, astronomers were interested in cyclical phenomena, whereas supernova explosions were considered to be atmospheric phenomena. Nevertheless, there is a doctor's account of a spectacular star appearing in the sky. All report that in July 1054, a star began to shine so brightly that it exceeded the brilliance of Venus. It remained visible in daylight for 3 weeks, and in the night sky for almost 2 years. 7 centuries later, in 1758, the famous Charles Messier searched assiduously for Halley's Comet and confused it with a small nebula in the Taurus constellation. To avoid further confusion, he decided to create a catalog of diffuse stars and assign the number 1 to this star. In 1928, Edwin Hubble made the connection between the Chinese astronomer's guest star and the Messier 1 nebula, the expanding cloud of gas released by the supernova of 1054. It's nicknamed the Crab Nebula. This nebula continues to grow at a speed of 1,500 kilometers per second, or 930 miles per hour, and will dilute in space over the coming millennia. Within the nebula remains the compact residue of the exploded star, the Crab pulsar. The pulsar is less than 1,000 years old. It generates electromagnetic radiation 100,000 times more intense than the Sun. This is what makes the central part of the Crab Nebula so bright. The nebula and pulsar form one of the most studied structures outside the solar system, as both are among the brightest objects in their respective categories. What's more, the date of the explosion is well known. SN 1054 is the most famous supernova in the history of astronomy. In winter in the northern hemisphere, it can be observed through a small telescope and appears as a pretty gray blob against the stellar background of the Milky Way. Supernova 2014J occurred in galaxy M82 in January 2014. It is a Type 1a supernova, and the closest to it discovered in over 40 years. To date, it remains the brightest supernova observed in the Cigar Galaxy for decades. It has been extensively studied in different wavelengths due to its unusual brightness and proximity. Far less spectacular than Type 2 supernovas, which are the endpoint of massive stars, whose remnant is usually a neutron star, Type 1a supernovas are produced by the explosion of much smaller stars, known as white dwarfs. Their explosions are said to be thermonuclear. At the end of the explosion, all that remains in space is a gigantic jet of particles known as afterglow. The supernova was discovered on January 21, 2014 by chance, while astronomer Steve Fosse was training his students to use a small telescope at the University of London Observatory. The scientists simply wanted to take advantage of a brief gap in London's cloud cover. He and his students then noticed a bright new star in the images taken of the Cigar Galaxy. The discovery was reported to the Astronomical Union's Central Astronomical Telegram Office, which confirmed that they were the first to spot this supernova. At the time of discovery, the supernova was 14 days from its maximum light, suggesting that it would become brighter over the following 2 weeks. It continued to get brighter until January 31st, when it had an apparent magnitude of 10.5. Quasars are the brightest sources of light in the universe. The word quasar comes from an English abbreviation meaning source of quasi-stellar radio radiation. These are extremely distant stars that look like very bright stars when observed through a telescope, but are actually examples of active galactic nuclei. Their impressive energy comes from the accretion of matter by rotating supermassive black holes that can contain millions to billions of solar masses. The black holes that sit at the center of galaxies are of an altogether different caliber to those produced by stars. While the latter sometimes reach the mass of the Sun, galactic black holes are millions, even billions of solar masses. The luminous power emitted by quasars can reach 10,000 times the total luminosity radiated by the hundreds of billions of stars in a galaxy the size of our Milky Way. However, most galaxies are not the site of such a violent outburst. Quasars are thought to gain power through the accretion of matter around supermassive black holes in the nuclei of these galaxies. No other mechanism seems capable of explaining the immense energies released and their rapid variability. But some phenomena remain unexplained to this day. For example, some relatively quiet galaxies seem to suddenly become quasars in just a few months. The remarkable luminosity of quasars is used as a tool for probing intergalactic space right up to the limits of the observable universe. Before reaching our telescopes, the photons emitted by quasars may encounter tenuous clouds of intergalactic gas on their billion light-year journey. Quasar absorption systems provide additional structural information to that provided by the distribution of galaxies. The growing number of known quasars, with their absorption spectra, enables more detailed statistical studies of the distribution and properties of intergalactic gas clouds and their relationship with dark matter and existing or forming galaxies. Absorption systems can be used to probe precise moments distributed throughout the history of the universe, but also to address essential issues in cosmology and even physics. The first quasars were seen as early as the late 1950s, and today there are over 100,000. Quasar 3C273 lies at an astronomical distance of 2.44 billion light-years, 1,000 times further away than the Andromeda Galaxy. It is located in the constellation Virgo. According to Hubble's law, and given its distance, this quasar is moving away at almost 50,000 kilometers per second, or 31,000 miles per second. The black hole at its center needs the equivalent of several hundred times the mass of the Sun per year to feed itself. It discharges some of this matter in the form of an immense jet. When it no longer has enough energy to feed itself, its host galaxy will revert to an ordinary star, and its luminosity will diminish. If there's one object in the universe renowned for its unprecedented violence, it's the quasar 3C186. This double quasar emits waves in all domains of light. It lies in the Lynx constellation, more than 8 billion light-years away. 3C186 lies at the heart of the galaxy, PGC 2817581. It has several special features. Its central light is offset by around 35,000 light-years from the center of the galaxy. This is due to the interaction between 3C186 and the second black hole inside it, The impact of these two supermassive black holes disrupts the galaxy, breaking it up and scattering its stars. The interaction between the two black holes is thought to have taken place 5 million years ago. Astronomers estimate that 3C-186 will leave the galaxy in around 20 million years. The result will be two supermassive black holes merging to form a black hole with a mass equivalent to 1 billion solar masses. The Earth has been hit by numerous asteroids. These collisions have played a major role in the history of its formation and evolution. Some 9 billion years have passed since the Big Bang. The local supercluster contains over 10,000 individuals. On its periphery, the local group is made up of some 50 galaxies, including the Milky Way, one of the largest. The Milky Way has a thin disk of stars and gas. This highly diluted gas concentrates in a few places, in much denser spirals. These interstellar clouds are opaque with molecules and grains of dust. One of them wanders proudly 27 light-years from the center of the Milky Way. Then, a fragment of this nebula collapses in on itself. The contraction transforms the globule into a protostar, and its energy into radiation. At its heart, the temperature rises so high that thermonuclear reactions cause hydrogen to fuse. A star is born, but not just any star, our Sun. Before its final contraction, the protostar is surrounded by a disk of gas and dust, which then divides into countless smaller bodies. Some agglomerate into larger structures. Matter spinning too fast to join the Sun in formation takes the form of a disk made up of gas, dust grains, and tiny aggregates of solid matter. The grains gradually stick together until they agglomerate into blocks. Under the effect of gravity, bodies over 1 kilometer in length are formed. The largest of these absorb everything within their sphere of influence. Planetary embryos are born. Their mass increases with distance from the Sun. Below the ice line, the environment is gradually emptied of gas, and the planetary embryos see their orbits lengthen to the point where they can cross each other. Violent collisions ensued, leaving only 4 of the planets, including Earth, intact. Barely scratched out of the ground, the Earth is already experiencing an eventful life. Our planet has cleaned up its orbital zone. The only exception is the 2 Lagrange points, L4 and L5, in the Earth-Sun system, which provide shelter for planetesimals attracted to the Earth during its formation. Point L4, for example, shelters a planetary embryo that continued to develop until it reached the size of today's Mars. Its name is Theia. Having reached too great a mass, Theia became unstable and escaped from its L4 equilibrium point. It then orbits the Sun until it collides with the Earth. Theia is totally shredded. Its pieces scatter all around. Its core, mainly iron, is buried in the heart of the Earth. 24 hours after impact, our future planet is surrounded by a disk of light rock from the 2 planetary mantles that collided. After a few years, these rocks agglomerate to form a new celestial object 20,000 kilometers or 12,500 miles from the Earth, which gradually moves away to become its satellite, the Moon. At first glance, this cosmic collision seems no more exceptional than any other. And yet, by giving the Earth such a large satellite capable of stabilizing its axis of rotation, this collision is paradoxically an essential event in the future evolution of life. The Moon plays a very important role in the existence of life on Earth. It exerts a major influence on the weather, the migrations of certain animals, the Earth's magnetic field, and in many other areas. It is also responsible for the 24-hour day. The Earth's tilt is kept stable by the Moon's gravity. If it weren't for the Moon, our planet would move up and down during its rotation. And if such wild movements were to take place, wind and clouds would move faster, and weather conditions would be extremely harsh and much less conducive to life. The phenomenon of the 4 seasons is also due to these changes in the Earth's rotation and axis. Without the Moon, the Earth would rotate on its axis in 8 hours instead of 24. The Moon's gravity slows down the Earth's movement, with enormous repercussions for the evolution of life on Earth. If a day lasted 8 hours, animal species would have had to adapt to rapid temperature changes and would certainly have evolved very differently. During the Moon's first days, solar winds were much more violent. At that time, the Moon was closer to the Earth, and its magnetic field was sufficient to protect its atmosphere and act as a shield against solar winds. If the Earth had no atmosphere, life as we know it today would not be possible. It contains the oxygen we breathe and protects us from ultraviolet rays and cosmic rays. The effect of the Moon's and Sun's gravity on the Earth slightly deforms the planet from front to back. This is what we call tidal forces, which cause ocean tides. Tides probably propelled the first forms of marine life onto land. Tides may also have influenced the Earth's plate tectonics. It is thanks to seismic activity that the planet's surface was able to cool and become habitable. "4 billion years ago, large-scale meteoric and cometary impacts hit the terrestrial planets. It was during the Apollo 15, Apollo 16, and Apollo 17 missions that this theoretical period in the history of the solar system was brought forward. The landing sites for these missions were established close to the great impact basins of the Sea of Rain, the Sea of Nectar, and the Sea of Serenity. Lunar rock samples were collected, and analysis on Earth revealed that their age ranged from 3.8 to 4.1 billion years, a relatively short period. These data were compared with the dating of other lunar meteorites recovered on Earth. Due to erosion, impact marks of ancient origin are very rare on our planet. Although this has long been interpreted as proof that the Earth's surface remained liquid for a long time, it would appear that in reality, the solidification time was much faster, and that the youth of the Earth's crust is due to the theory of the late Great Bombardment. At the start of the solar system's formation, the 4 giant planets were much closer together than they are today. Uranus is the furthest from the Sun, and lies close to the inner edge of a planetesimal-rich disk. Barely 600 million years after the formation of the solar system, the gas giant planets began to migrate due to gravitational interactions with the famous small objects that remain at the inner edge of the disk. Saturn, Neptune, and Uranus are moving strongly inwards, and Jupiter more moderately. Jupiter's rotation period around the Sun is half that of Saturn. This movement completely destabilized the solar system, and collisions between small bodies and the terrestrial planets increased. It was the beginning of chaos. Saturn was pushed back into its final orbit by Jupiter, and collided with Neptune and Uranus. The latter two are expelled into much more elongated orbits. They plunge into the planetesimal-filled disk, ejecting thousands of planetesimals far from their original orbits. For the most part, these small bodies fly outside the solar system, giving rise to the Kuiper Belt, among others. But some of them head inland. The 4 terrestrial planets, as well as the Moon, are the victims of numerous brutal impacts. The Earth is said to have been hit by 22,000 giant meteorites. Some asteroids were larger in diameter than France. The oceans that covered the Earth's surface were partially vaporized. Mercury, the Moon, and Mars bear the scars of this massive bombardment. On Mars, the Hellas Planitia impact basin has been linked to the Great Lake bombardment by analysis of lunar samples. The basin measures around 2,200 kilometers, or 1,400 miles in diameter, and 9,500 meters, or 31,000 feet in depth. It is the largest impact structure on Mars visible from Earth. The basin appears as a bright area due to the high albedo of the dust constantly stirred up by the winds. The Hellas Planitia basin is surrounded by relief created by the impact. For over 1,000 kilometers, the terrain was raised. To the west, the edge of the basin is marked by a mountain range. In places, it reaches an altitude of 2,000 meters or 6,500 feet. To the east, the edge is marked by valleys, representing the beds of large rivers that have now dried up. Water was abundant in the impact basin. On the planet Mercury, the Caloris Basin is the most massive meteor crater known to date. It is located at one of the planet's 2 hot poles. Measuring around 1,550 kilometers, or 960 miles in diameter, it was formed by the fall of an asteroid with a diameter of around 150 kilometers, or 93 miles. The basin is surrounded by mountains that rise to almost 2 kilometers, or 1 mile in height. Its floor is filled with cooled lava, reminiscent of lunar pools. For some 1,000 kilometers or 620 miles, the material ejected by the impact forms rings surrounding the basin. The impact that formed the Caloris Basin is thought to have triggered volcanic activity on Mercury. The impact is also thought to have released heavy elements such as sodium and potassium from the planet's mantle. Being around 130 kilometers or 80 miles deep, elements could have been brought up from the mantle during readjustment movements. On the Moon, the Mer Orientale and the Mer des Pluies are basins that would also have been dug during the Great Lake bombardment. The Mer Orientale is a lunar sea formed by the impact of a meteorite, which raised the mountains bordering the crater. It is one of the Moon's most impressive structures, with a diameter of around 900 kilometers, or 560 miles. 2 mountain ranges encircle the Mer Orientale. The Montes Rook, measuring 700 kilometers, or 430 miles in diameter, and the Montes Cordillera, measuring 900. The Sea of Rains is a sea found on the visible side of the Moon, formed when liquid lava filled a giant pre-existing impact crater, called the Basin of Rains. The latter is surrounded by 3 mountain rings, each composed of several mountain ranges. For some 800 kilometers or 500 miles, an area is covered by ejecta, forming a region of numerous reliefs. Asteroid impacts are common phenomena in the solar system. 160 million years ago, a collision between 2 large objects in the asteroid belt produced numerous fragments, known as the Baptistina family. The first body is located on the inner edge of the asteroid belt, just over 2 astronomical units from the Sun. Despite the fact that its growth is limited by the disruptive presence of Jupiter, it boasts a diameter of 170 kilometers or 100 miles, a very respectable size. It is one of the largest asteroids in the main belt. The second body involved in the collision is another asteroid, 60 kilometers or 37 miles in diameter. Its orbit is similar to that of the first asteroid. One day the two collide. The impact occurs at a speed of 3 kilometers per second, or 1.8 miles per second. It was so violent that the two asteroids were reduced to a dust of debris, which aggregated again to form a family of objects with similar orbital characteristics. This is the Baptistina family. This asteroid family comprises some 2,500 known members. Many years ago, we thought that some of them were responsible for remarkable cosmic collisions, such as the one that caused Tycho's crater on the Moon, or a direct collision with the Earth 66 million years ago. However, data from the Wide Field Infrared Survey Explorer in 2011 challenged this hypothesis, suggesting that the Baptistina family had in fact formed much more recently than previously thought, as recently as 80 million years ago. Consequently, the origin of the impactor that caused the extinction of the non-avian dinosaurs remains an unsolved mystery. Further study and exploration of the asteroid belt may one day unravel this mystery and help us understand the forces at work that triggered these impacts. Asteroids can undergo an effect that affects their rotation on themselves in the presence of radiation. When the object's face is illuminated by the radiation source, it receives energy. After half a revolution, this same face then goes into shadow, radiating outwards the energy it has previously received. The result is a very slight thrust exerted on the object, depending on its shape and surface condition. This is known as the Yarkovsky effect, named after the Russian engineer who discovered the phenomenon. Many individuals are then disrupted by Jupiter and the other planets. They find themselves injected into orbits that lead them to cross those of the Earth and Moon. 108 million years ago, an asteroid measuring 10 kilometers or 6 miles in diameter swung low over the Moon's western horizon and collided with it. The impact creates a huge impact crater called Tycho. This sends thin cracks across the Moon's southern hemisphere, extending to over 1,000 kilometers or 620 miles in all directions. The crater is located in the southern lunar mountains. It has well-defined contours, and its interior is characterized by a high albedo. The crater's diameter is 82 kilometers or 50 miles, and its rim rises to 4.7 kilometers or 3 miles above floor level. At that time, from Earth, it was the dinosaurs who witnessed this cosmic collision. Little do they know that they will be the next victims of these cosmic events. The Chicxulub crater is the most famous asteroid impact on Earth. It occurred around 66 million years ago in Mexico's Yucatan Peninsula and is associated with one of the world's largest mass extinctions. The impacting asteroid measures around 10 kilometers in diameter. On contact with the Earth, it formed a crater 180 kilometers, 112 miles in diameter. This suggests an explosion power several billion times that of the Hiroshima bomb. The crater basin is covered by about 1,000 meters, or 3,300 feet of limestone. It extends under the mainland and the Gulf of Mexico. Scientists are trying to explain what really happened during the impact that caused the demise of those who reigned supreme at the time, the dinosaurs. At the time, these gigantic, majestic animals had dominated the planet's animal ecosystem for 165 million years. They are the most imposing creatures the Earth has ever sheltered. Dinosaurs are very diverse and are found all over the planet. An asteroid in a region between the orbits of Mars and Jupiter is projected at several kilometers per second. It heads straight for the Earth until impact, forming a huge crater. The energy released was so intense that the rock of the Earth's crust liquefied. In less than a second, all the water within a 60-kilometer radius of the impact turns to steam. Animals in the vicinity are instantly killed. A few seconds after impact, the shock wave releases an unbearable heat that crosses the ocean. Everything in its path evaporates or melts. It would take just a few years for life to reappear in the impact crater, but over 30,000 years for a thriving ecosystem to develop. Scientific research has revealed the presence of burrows dug by shrimps and worms, as well as microfossils of plankton and algae. This suggests that the crater became habitable shortly after impact, even though the mass extinction was not yet over. Evidence of this impact was confirmed just before the 1980s. A thin black layer of clay just a few millimeters thick was revealed in some of the geological layers between the Cretaceous and Tertiary strata. This geological boundary contains abnormal levels of iridium. Although rare on Earth, iridium is found in abundance in certain meteorites. Scientists sometimes find minute quantities of iridium in terrestrial sedimentary rocks due to the fine, micrometeorite showers that are frequent on the planet. But analysis of this Cretaceous Tertiary layer reveals far more. This is why it has been suggested that the planet must have suffered the fall of a huge meteorite. At the time, the crater could not be found. In 1981, two geophysicists employed by the Mexican oil company Petróleos Mexicanos investigated the Yucatan and discovered this unusual geological structure. The fall of this meteorite marked the end of the Cretaceous period and was responsible for a climatic upheaval that led to the extinction of non-avian dinosaurs and a large proportion of the animal and plant species at the time, both on land and in the seas. Without this event, Earth's history would be totally different, and we certainly wouldn't be here to talk about it. The Vredefort Dome is the largest known impact crater on Earth. It is located in South Africa, in the territory of the Free State Province. In 2005, Vredefort Dome was inscribed on UNESCO's World Heritage List for its scientific and scenic interest. The town of Vredefort was built inside the impact crater. The asteroid's impact dates back 2 billion years. Until recently, it was the oldest known impact crater on Earth, until the discovery of Manliksok crater in Greenland, estimated to be 3 billion years old. The asteroid's diameter has been estimated at 15 kilometers or 9 miles. It left a crater with a diameter of around 300 kilometers or 186 miles. Vredefort is one of the few craters to feature multiple terrestrial rings, a phenomenon often destroyed by erosion and plate tectonics. The dome is only the central part of the astrobleme, which actually extends over 360 kilometers or 224 miles in length, from Johannesburg to Welcome in the Free State. South Africa's geological stability has ensured the crater's continued existence. It is one of the only craters to have been crossed by a river, the Vaal, for almost 280 million years. the asteroid's impact would have really damaged the planet, causing fires all over the world. The enormous quantity of dust thrown into the atmosphere would have altered the climate for years. Located in Ontario, Canada, the Sudbury Basin is a crater formed some 1.85 billion years ago. It is the second largest known impact crater on Earth, but also one of the oldest. It is located on the Canadian Shield in the city of Greater Sudbury. The Sudbury Basin is 62 kilometers or 39 miles long, 30 kilometers or 19 miles wide, and 15 kilometers or 9 miles deep. The diameter of the meteorite has been estimated at around 10 kilometers. Some of the rock fragments ejected on impact traveled more than 800 kilometers or 500 miles and were scattered over an area of 1.6 million square kilometers. Scientists even suggest that such an impact may have scattered debris around the world, but that it has since been eroded away. The impact that created the Maniksok crater is thought to have occurred around 3 billion years ago. It is the oldest known terrestrial meteorite crater, yet remains totally invisible today due to erosion. By analyzing the nature of the rocks, scientists were able to prove that it was an asteroid impact. The asteroid would have had a diameter of around 30 kilometers or 19 miles and would have hollowed out a crater originally 600 kilometers or 370 miles in diameter. At the time, only bacteria were beginning to populate the planet, but if such an object hit us today, it would exterminate all forms of life on Earth. Also known today as Meteor Crater, Barringer Crater is located in Arizona, USA, 60 kilometers or 37 miles east of Flagstaff. It is a well-preserved crater formed by the impact of a small asteroid around 50,000 years ago. At the end of the Pleistocene, an object of peculiar composition hurtled towards the Earth. Made of iron and nickel, it is more likely to be a fragment of a planet core in the process of forming than a small body from the early solar system. As a result, it is much more resistant to the stresses imposed by the Earth's atmosphere than blocks of rock or ice. Once it reaches an altitude of around 14 kilometers or 9 miles, it eventually breaks up under the effect of increasingly dense layers of air. The meteorite splits into two parts, with a block of half its initial mass on one side and smaller fragments surrounding the initial impact over a diameter of 200 meters or 660 feet on the other. The main block, weighing 300,000 tons, hits the Earth at a phenomenal speed at 12 kilometers per second or 7 miles per second. The collision forms a crater over a kilometer in diameter. At the time, this area was grassy savanna occupied by mammoths and sloths. The impact releases energy equivalent to that of a thermonuclear explosion. All life is destroyed within a radius of several kilometers due to the blast and heat generated by the collision. The impact did not cause any noticeable change in the planet's climate. Meteor Crater is bowl-shaped, measuring almost 1,400 meters or 4,500 feet in diameter, and 190 meters or 620 feet deep. Today, it is a popular tourist attraction. Warburton Crater is located in Australia near the town of Ora Banda. Its diameter is around 5 kilometers or 3 miles. The asteroid's impact is thought to have taken place 100 million years ago during the Cretaceous, well before the impact that formed the famous Chicxulub crater. The Warburton crater was discovered in a very flat landscape. Erosion has taken its toll, and there's no sign of a crater on the surface. The impacting asteroid must have been between 100 and 200 meters in size, or between 330 and 660 feet in diameter. The crater is buried under several kilometers of sediment. It is not a single impact crater, but two craters, 200 kilometers or 125 miles wide, forming a structure 400 kilometers or 250 miles in diameter. The two impacts may have occurred simultaneously due to the fragmentation of an asteroid. The Populated crater is located in Siberia. It is the fourth largest known terrestrial impact crater, with a diameter of around 100 kilometers. It was formed by a meteorite impact 35.7 million years ago, during the Upper Eocene. It has been designated a geopark by UNESCO as a site with a specific geological heritage. Populated is also the world's largest diamond mine. During the Cold War, it was kept secret for decades. Shock waves from the impact would have instantly transformed graphite into diamonds within a radius of 14 kilometers or 9 miles. This mine would contain the equivalent of 10,000 billion carats. Just over 200 million years ago, an asteroid hit the north shore of Quebec in Canada, forming the Manicouagan crater. It is one of the oldest and largest impact craters on the planet. Due to erosion caused by glaciers, it is not easily visible on the Earth's surface. Its concentric structure, around 100 kilometers or 62 miles in diameter, is explained by the shock waves transmitted during the impact. The meteorite responsible measured around 5 kilometers or 3 miles in diameter. Comet Shoemaker-Levy, sometimes abbreviated SL9, is famous in astronomy for being the first to offer direct observation of a collision between two solar system objects outside the Earth. It has been closely observed by astronomers from all over the world. Comet Shoemaker-Levy broke up as it approached the planet Jupiter, colliding with it in July 1994. This collision led to the discovery of new elements about Jupiter and highlighted its key role in reducing the amount of space debris in the solar system. This comet is unusual in that it has been orbiting Jupiter for some time, rather than orbiting the Sun, like all the other comets known at the time. By 1992, it had already passed very close to Jupiter, just over 40,000 kilometers or 25,000 miles from the cloud tops. The 1994 collision was by far the closest and resulted in the comet's fragmentation. Each fragment is designated by a letter, ranging from fragment A to fragment W. The 1994 encounter was eagerly awaited. Astronomers had prepared their terrestrial telescopes, and several space observatories were ready to observe the impact live. On July 16, 1994, at just over 8 p.m., fragment A struck the southern hemisphere of Jupiter at a speed of around 60 kilometers per second, or 37 miles per second. A fireball then formed. A fireball was formed reaching a temperature of around 24,000 degrees Celsius, or 43,000 degrees Fahrenheit, before dropping rapidly to around 1,500 degrees Celsius, or 2,700 degrees Fahrenheit. After this initial impact, observers see a huge black spot. These were the effects of impact debris. Over the following week, 21 impacts were recorded, the largest of which was produced by Fragment G. It took place on July 18th at around 7:30 a.m., creating a giant dark spot over 12,000 kilometers or 7,500 miles wide. On July 22nd, the final fragment, fragment W, struck Jupiter. Direct observation of this collision provided a wealth of information about Jupiter. The planet has since been regarded as a kind of cosmic vacuum cleaner within the solar system. Jupiter's strong gravitational influence attracts numerous small comets and asteroids. Its impact rate is estimated to be between 2,000 and 8,000 times greater than that of our planet. In other words, if it weren't for Jupiter, asteroid impacts on the other planets in the solar system would be far greater. Astronomers have even gone so far as to hypothesize that without Jupiter to intercept potential impacts, collisions leading to mass extinctions, such as the cosmic impact that caused the Chicxulub crater, would be much more frequent, and Earth would certainly not have been able to witness the development of complex life forms. To explore the Virgo supercluster, we have to leave our solar system, then our Milky Way galaxy, then the local group, the group of galaxies in which the Milky Way lies. The local group is one of the groups of galaxies that make up the Virgo supercluster. We are now at the heart of this supercluster, some 200 million light-years across. The Virgo supercluster is also known as the local supercluster. It's called the Virgo supercluster because it contains the Virgo cluster at its center. The Virgo cluster is located around 65 million light-years from us. The discovery of the Virgo supercluster was a gradual process. In 1863, William and John Herschel published the first major collection of nebulae, revealing that a large number lay in the region of the Virgo constellation. Nearly a century later, the Franco-American astronomer G.H. de Vaucouleurs then hypothesized that this excess of nebulae was in fact a galaxy-like structure, but on a larger scale. In 1953, he called this structure a local supercluster, and in 1958, a local supercluster. In the 1960s and 1970s, the scientific community was not yet unanimous on the nature of this structure, which could just as well be a random alignment of galaxies as an ordered structure. In the 1970s and 1980s, a redshift analysis showed that it was indeed a structure. The mass of the local supercluster was estimated at 10 to the 15th power solar masses. Much of this would be dark matter, since the supercluster's luminosity seems very low in relation to the number of stars in it. Contrary to long-held belief, the Virgo supercluster is not a gravitational structure with a clear boundary. In fact, the galaxies in this supercluster are not gravitationally attracted to the center of the structure, the Virgo cluster. Instead, they are attracted to a strange object outside this structure called the Great Attractor. We'll come back to this at the end of our journey. Incidentally, the Virgo supercluster is only a portion of a larger whole called Laniakea. Superclusters therefore appear to be structures of galaxies attracted to a large attractor, rather than structures of galaxies gravitationally bound together. Let's take a moment to study the structure of the Virgo supercluster before exploring its galaxies. In 1982, American astrophysicist Brent Tully illustrated the basic structure of the local supercluster. It would consist of a disk and a halo. The disk is roughly the flattened shape of a pancake and contains 2/3, or around 60%, of the supercluster's luminous galaxies. It includes 3 galaxy cluster subgroups: the Virgo cluster, the Hound Cloud, and the Virgo 2 cloud. The halo comprises a third of the remaining elements, including many elongated objects. It's a more or less spherical halogen atom. The eastern local supercluster has no high-density nucleus. Where is the local group, and therefore our galaxy, located in this immense structure? The local group is located near the edge of the supercluster, in a small filament. It is attracted by the Virgo cluster, not the center of the supercluster. We're now going to look at the galaxies in the local supercluster. Astronomers have noticed that the elements of this supercluster are not arranged randomly. The density of galaxies decreases with the square of the distance from its center, located near the Virgo cluster. The majority of bright galaxies, i.e. those with an absolute magnitude greater than -13, are concentrated in just a few clouds. In fact, just 11 clouds concentrate 98% of the bright galaxies, including the Hound Cloud, the Virgo cluster, Virgo groups 2 and 3, and Leo group 2. All in all, there are some 10,000 galaxies in the local supercluster, spread across some 100 clusters. Let's begin our journey into the heart of the Virgo supercluster by exploring the local group, where our galaxy is located. The local group is located on the outskirts of the Virgo supercluster. It comprises more than 50 galaxies. It is not possible to determine with certainty the number of galaxies in this group, as some are very faint and therefore difficult to detect, and the boundaries of the local group are not yet precisely defined. It is estimated to extend over a diameter of around 10 million light-years. In fact, it's considered a small structure, even if this may surprise you. So there could be far more than 50 galaxies in the local group, perhaps 60 or 80. What we do know is that the local group is organized around two spiral galaxies, the Andromeda Galaxy, or M31, and the Milky Way. Each of these two spiral galaxies is surrounded by satellite galaxies. For example, the galaxy closest to the Milky Way is the Great Dog Galaxy, located just 25,000 light-years from our own galaxy. A third spiral galaxy has been observed in the local group, the Triangle Galaxy, or M33. It is considered a satellite galaxy of the Andromeda Galaxy. In the local group, you can also observe two Magellanic spiral galaxies, i.e., single-armed spiral galaxies, the Large Magellanic Cloud and NGC 3109. These galaxies are smaller than ordinary or barred spiral galaxies. You can also observe an elliptical galaxy, M32, also a satellite of the Andromeda Galaxy. Elliptical galaxies contain only old stars, so according to astrophysicists, they are the result of the collision of two spiral galaxies. The local group also contains two dwarf elliptical galaxies, M110 and NGC 147. All the other galaxies in the local group are either spheroidal dwarf galaxies or irregular galaxies. Spheroidal dwarf galaxies are small, more or less spherical galaxies, often found in galaxy clusters. They are ancient galaxies that closely resemble globular clusters. Irregular galaxies, on the other hand, are neither spherical, elliptical, nor spiral-shaped. They are very luminous, rich in bright stars, but often too small to be easily detected. According to astronomers, they were once very numerous in the universe, but collisions have reduced their numbers. As a result, they now make up just 10% of the galaxies in the observable universe. Let's take a look at the Andromeda Galaxy, the largest galaxy in the local group. With a diameter of 220,000 light-years, it is larger than the Milky Way. It contains 2 to 5 times as many stars as the Milky Way, i.e., around 1,000 billion stars. As a result, it is 25% brighter than our own galaxy. But perhaps this won't last, as the Milky Way's star formation rate is 3 to 5 times higher than that of the largest galaxy in the local group. The Andromeda Galaxy is located in the Andromeda constellation, 2.55 million years from us. You can observe it with a naked eye from the northern hemisphere. It is thought to have been formed by the collision of 2 galaxies not so long ago. Astronomers estimate its formation date at less than 3 billion years ago, at a time when the Earth already existed. The Andromeda Galaxy and the Milky Way are approaching each other and will collide in around 4.5 billion years' time. The 2 galaxies will then merge to form a giant elliptical galaxy, along with their 2 central, supermassive black holes. The Andromeda Galaxy includes numerous satellite galaxies, notably the Triangulum Galaxy, the 3rd largest galaxy in the local group. The 2 are separated by a distance of 750,000 light-years. This galaxy is unusual in that it has an HII region at its center, rather than a supermassive black hole, which is the most powerful X-ray source in the local group. The Milky Way, the 2nd largest galaxy in the local group, is home to between 200 and 400 billion stars and over 100 billion planets. The solar system is located on the periphery of the galaxy's center, the supermassive black hole, Sagittarius A, precisely 27,000 light-years away. It's interesting to note that the Sun takes around 250 light-years to circle the center of the galaxy, so it's only been around 20 times since it came into existence. Our galaxy formed longer ago than the Andromeda Galaxy. Astronomers estimate its formation at 800 million years after the Big Bang. The oldest star in the Milky Way, HE 1523-0901, is thought to have formed shortly after the Big Bang, 13.2 billion years ago. Among the Milky Way's satellites is the Big Dog Dwarf Galaxy, the closest to us, located just 25,000 light-years away. This irregular dwarf galaxy contains just 1% of the Milky Way's stars and is being blown to smithereens by the tidal forces of the Milky Way. It is very likely that in the future, it will disintegrate completely. The closest group of galaxies to the local group is the Sculptor group, or Sculptor filament. This group includes the irregular galaxy NGC 55 and the spiral galaxies NGC 247, NGC 253, NGC 300, and NGC 7793. All are very bright, although you won't be able to see them with the naked eye from Earth. irregular galaxy NGC 55 lies at the boundary between the Sculptor filament and the local group, and is therefore the closest to us, at a distance of around 6 million light-years. It contains many stars in formation. NGC 253 is the dominant galaxy in the Sculptor filament, being the largest and brightest. You may have already seen the image taken by ESO's VISTA telescope at the Paranal Observatory in Chile. This image is impressive for its sharpness and precision. It's probably the most detailed wide-field image ever made of the Sculptor's filament. VISTA can see through the dust thanks to its infrared vision, resulting in a sharp, precise image. NGC 253 is also known as the silver dollar or silver coin galaxy. It is an intermediate spiral galaxy located in the southern constellation of the Sculptor, around 11 million light-years from us. It was discovered by German-English astronomer Caroline Herschel in 1783, while searching for comets. From Earth, you can observe it with binoculars, as it's one of the brightest galaxies in the sky after our neighbor Andromeda. You can see it from the edge and make out its spiral arms and luminous core. NGC 253 is a good example of a starburst galaxy, i.e., a galaxy that is forming stars at a high rate. This process was probably triggered by numerous supernova explosions. In fact, you can see many bright clusters scattered around the galaxy. They're a kind of star nursery. You can see very young, hot stars that have just ignited, baby stars as it were. In the famous photo of NGC 253, we can clearly see that the radiation from these newly formed stars makes the surrounding clouds of ionized hydrogen glow. NGC 247 is also part of the Sculptor group. It is a faintly barred intermediate spiral galaxy in the Whale constellation. It was discovered by the German-British astronomer William Herschel in 1784, the brother of Caroline Herschel, who discovered the Sculptor galaxy. This galaxy is relatively unknown, as it is rather difficult to observe and photograph. A large instrument would be needed to obtain an image with enough contrast to clearly distinguish the galaxy. NGC 7793 is also a spiral galaxy in the Sculptor filament and the Sculptor constellation. It is one of the brightest galaxies in the group. Studies carried out by the Chandra Space Telescope have shown that this galaxy contains 22 X-ray sources, the majority of which are located in the Eastern Hemisphere. This may be explained by interaction with a nearby galaxy in the past. Before we set off to discover another group of galaxies close to our local group in the Virgo supercluster, let's take a look at the Sculptor dwarf galaxy, which was the first spheroidal dwarf galaxy to be discovered orbiting the Milky Way. Long thought to be part of the Sculptor filament, it is now considered a satellite galaxy of the Milky Way. It is thought to be located around 280,000 light-years from Earth, but was only discovered relatively late, due to its low luminosity. The galaxy contains stars that are poor in heavy elements and therefore old. It is therefore an interesting galaxy for astronomers, as it may reveal valuable clues to the history of the earliest periods of star formation in spheroidal dwarf galaxies. We will now explore the IC 342 Maphei group, another group of galaxies close to the local group. Like our galaxy group, it is organized around two substructures made up of massive galaxies, IC 342 and the pair formed by the two galaxies MAPHI-1 and MAPHI-2. IC 342, also known as Caldwell 5, is an intermediate spiral galaxy located 11.4 million light-years from us in the Giraffe constellation. It is the most luminous and massive galaxy in the group. It was discovered in the 1890s. Like NGC 253, it is a star-forming galaxy. The IC 342 subgroup includes 9 known satellite galaxies, including NG 1560, the Giraffe A galaxy, also known as Camelopardalis A or Cam-A, and the Giraffe B galaxy, also known as Camelopardalis B or Cam-B. MAPHI-1 and MAPHI-2 are located in the constellation Cassiopeia. They were discovered rather late by Italian astronomer Paolo Maffei in 1968. Their discovery was not easy, as they were both hidden behind the plane of our galaxy and therefore partly obscured by interstellar matter. MAPHI-1 is the closest of the large elliptical galaxies to us, while MAPHI-2 is a spiral galaxy with a very pronounced bar. Like IC 342, the MAPHI-1 and MAPHI-2 pair has 9 known satellite galaxies, including Dwingaloo 1 and Dwingaloo 2, a barred spiral galaxy and its satellite, a small irregular galaxy. Both are located in the Cassiopeia constellation and were discovered late in 1994. Indeed, they are located at very low galactic latitude, in the avoidance zone, i.e. the area of the sky that is heavily obscured by the dust of the Milky Way. We're now in the Big Dipper. What you're looking at is the group formed by the galaxy pair M81, M82, and NGC 2403. M81 and M82 were discovered in 1774 by German astronomer Johann Elert Bode. Spiral galaxy M81 is the largest of the group, with a diameter of around 87,000 light-years. Although it can't be seen with the naked eye from Earth, it remains one of the brightest galaxies in the sky, which you can observe with binoculars. M82, also known as the Cigar Galaxy, is also a spiral galaxy. It is 5 times brighter than the Milky Way, and even 100 times brighter at its center. And with good reason. M82 is a veritable nursery of stars. A few million years ago, it is thought to have brushed against M81, triggering a huge wave of star formation in this galaxy. It's the closest star-forming galaxy to Earth, so it's much studied by astronomers. It was also in this galaxy that astronomers discovered the brightest pulsar known to date, the ultra-luminous X-ray source M82X2, in 2014. M82X2 is located 12 million light-years from Earth and emits an energy equivalent to 10 million times that of the Sun. M81 and M82 are in close gravitational interaction with NGC 3077, causing the formation of atomic hydrogen filaments between these galaxies. NGC 2403 is the second most important galaxy in the M81 group. It is an intermediate spiral galaxy discovered in 1788. Half the size of the Milky Way, it is home to numerous star-forming nebulae. You can clearly see its spiral arms, as well as small spots resembling star clusters. This was the first galaxy outside our local group in which a Cepheid was discovered. Cepheids are giant variable stars, or yellow supergiants, 4 to 15 times more massive than the Sun, and 100 to 30,000 times more luminous. 2 supernovas 16 times more luminous than average were also detected in this galaxy in late 2004. At that time, the galaxy's luminosity was more than 500 million times that of the Sun. The M101 group lies between the Big Dipper and Hound constellations. It is centered on the galaxy M101, the closest of the giant spiral galaxies, and contains at least 80 galaxies. M101 has a diameter of over 250,000 light-years, twice that of the Milky Way. It is one of the 10 largest galaxies in the Virgo supercluster. It is also known as the Windmill Galaxy, or NGC 5457. Viewed from the front, when he discovered it, astronomer Pierre McCain described it as a starless nebula, very dark and very large. Yet M101 is said to contain 1,000 billion stars, 10 times more than the Milky Way. This group of galaxies also includes M51, or the Whirlpool Galaxy. M51 has recently moved closer to the galaxy NGC 5195, scattering billions of stars from NGC 5195 into intergalactic space and accentuating M51's spiral arms. NGC 5474 is also in the M101 group and may have collided with this galaxy in its recent history. It is a deformed spiral galaxy. Its nucleus is now very far from the center of its disk. NGC 5204 is a small, Magellanic spiral galaxy that emits a very powerful, ultraluminous X-ray source, discovered in 1980 by the Einstein Observatory, whose origin has yet to be identified. It could be an intermediate mass black hole. Finally, the group also includes the intermediate spiral galaxy NGC 5585, which has the particularity of having a much higher proportion of dark matter than other galaxies of the same type. We're now in the Centaur constellation. In front of you is the lenticular galaxy Centaurus A, or NGC 5128. It's the fifth brightest galaxy in our sky, and one of the closest radio galaxies to Earth. As a reminder, a radio galaxy is one in which most of the energy emitted comes from radio waves, rather than the usual components of a galaxy, such as stars, dust, or interstellar gas. Astronomers are therefore carefully studying its active galactic nucleus. In radio waves, Centaurus A extends over 20 times the apparent diameter of the Moon. Observations of this galaxy suggest that it swallowed a spiral galaxy around 500 million years ago, which would explain its intense radio emissions. Centaurus A's appearance is so strange that it wasn't until 1952 that it was classified as a galaxy. Seen from Earth, it resembles a lenticular or elliptical galaxy with a band of dust superimposed. Again, this strange morphology can be explained by the merging of two smaller galaxies in the past. While the bulge of the galaxy contains mainly old red stars, the disk contains over 100 star-forming regions. The Centaurus A galaxy forms a galactic group with the two spiral galaxies, M83 and NGC 4945. M83 is located in the Hydra constellation and is often nicknamed the Southern Windmill Galaxy for its resemblance to M101. At its heart lies a star-forming outburst region, which is disrupted by a supermassive black hole that ingests huge quantities of matter while expelling matter and energy outwards. This is the galaxy that gave its name to the French electronic music group M83. As for NGC 4945, It's a barred spiral galaxy in the constellation Centauri that resembles the Milky Way. There are a few differences, however, which observations have revealed despite the galaxy being viewed from the edge. Its center is much brighter than that of the Milky Way, and it is believed to house a supermassive black hole that also ejects energy into space, while devouring huge quantities of matter. It has a highly active nucleus, meaning that its central bulge emits more energy than quieter galaxies. It is therefore classified as a Seyfert galaxy. We now turn to a spiral galaxy in the Peacock constellation, NGC 6744. It is accompanied by an irregular companion galaxy, NGC 6744a, which superficially resembles one of the Magellanic Clouds. Located 30 million light-years from us, NGC 6744 is considered to be a look-alike of our own Milky Way, although its diameter is twice that of our galaxy. It is one of the largest and closest spiral galaxies to Earth. Its apparent size in the sky is 2/3 the size of the full moon. Like the Milky Way, NGC 6744 has a dense, elongated central nucleus, a disk of dust, and spiral arms. Astronomers have identified at least 6 galaxies that belong to the same group as NGC 6744. Our discovery of the Virgo supercluster continues with the galaxy NGC 7582. This spiral galaxy lies around 70 million light-years from Earth, in the constellation of the Crane. This galaxy was photographed by the MUSE instrument on ESO's Very Large Telescope to study the effect of an active black hole on star formation in a galaxy. Indeed, the central black hole of NGC 7582 feeds an active core thanks to the enormous quantities of energy it releases. The study of NGC 7582 shows that a structure surrounds the central supermassive black hole, diverting the flow of energy from the active core in the form of powerful winds to protect the rest of the galaxy. NGC 7582 is considered a variable active galaxy. In 1998, a sudden and unusual change in its optical emission line spectrum was observed for several months. Among the hypotheses put forward to explain this variation, astronomers considered the capture of a star by the supermassive black hole. Today, however, it is thought to be molecular material orbiting the active center, periodically occulting it, which gives rise to these variations. NGC 7582 is also thought to be a star-forming galaxy, with one strong burst occurring 6 million years ago and another 1 billion years ago. NGC 7582 is part of the Crane Quartet with 3 other galaxies, NGC 7599, NGC 7590, and NGC 7552. We're now in the constellation of Perseus. You're looking at the barred lenticular galaxy NGC 1023, discovered in 1786 by William Herschel. It's one of the brightest galaxies to be seen, just outside the Milky Way. With a diameter of around 60,000 light-years, it contains a supermassive black hole of around 44 million solar masses at its center. It's small enough to be difficult to see from Earth. You'd need a small telescope, a clear, pollution-free sky, and a time when the moon is faint or distant. The NGC 1023 group includes at least 19 galaxies in the Perseus, Andromeda, and Triangulum constellations. Most of these galaxies are either small spiral galaxies or dwarf galaxies. For example, spiral galaxy NGC 891 is the largest galaxy in the NGC 1023 group, with a diameter of 131,000 light-years. Seen from the edge, this galaxy in the Andromeda constellation is best known to astronomers for being the site of one of the brightest supernovas ever observed, SN 1986J. This supernova, discovered on August 21, 1986, had an apparent magnitude of 14. The Virgo cluster is located at the center of the local supercluster. According to astronomers, it is the largest group of galaxies within a radius of 100 million light-years. The cluster is thought to contain between 1,300 and 2,000 galaxies, including 150 large galaxies and a large majority of dwarf galaxies. The diameter of the Virgo cluster is 15 million light-years. Even the local group is smaller than the Virgo cluster and is gravitationally attracted to it. The Virgo cluster is organized around three main subclusters formed by the galaxies M87, M86, and M49. M87 is the largest galaxy in the cluster, with a diameter of 120,000 light-years. This giant elliptical galaxy contains over 10 billion stars, a supermassive black hole of 6.5 billion solar masses, and more than 10,000 globular clusters. M87 is surrounded by numerous satellite galaxies, including M98, M99, and M100, and the pair of galaxies known as the I galaxy. As for the elliptical galaxy M86, it has the particularity of approaching the Milky Way at high speed. In fact, it's the second fastest approaching galaxy after M90, at a speed of 227 kilometers per second, or 140 miles per second, according to the NED database. It is also said to contain almost 3,800 globular clusters. Finally, the third major elliptical galaxy in the Virgo cluster is M49. It's smaller than M87, but still quite large, with a diameter of 124,000 light-years. Far from the cluster's center, it is nevertheless the brightest galaxy, and therefore the first to have been discovered in the Virgo cluster. It contains some 200 billion stars and 6,300 globular clusters. The M49 group contains more than 120 galaxies in the Virgo and Bernice constellations, including the elliptical galaxy M60, which astronomers believe could constitute a fourth subcluster in its own right. In the Big Dipper constellation on the flank of the Virgo cluster, we find a group of galaxies known as the Big Dipper cluster or Big Dipper group. Its luminosity is 30% that of the Virgo cluster, and its mass only 5%. This cluster forms a ribbon of galaxies in the northern hemisphere, most of which are spiral galaxies. The Big Dipper cluster is made up of two main groups. Ursa Major North comprises most of the cluster's large galaxies, located above 50 degrees north. This boundary remains rather arbitrary. The three brightest galaxies in the Ursa Major North group are NGC 3631, NGC 3953, NGC 4088, and M109. But these are not the only bright galaxies in the group. There are 32 galaxies with a diameter of over 30,000 light-years in this group. The second group in the Big Dipper cluster is Ursa Major Sud. Schematically, this group comprises galaxies located south of 50 degrees. The three brightest galaxies in the Ursa Major South group are NGC 3675, NGC 3726, and NGC 3938. The Virgo 2 groups are long filaments of galaxies stretching southwards from the edge of the Virgo cluster. In fact, they are a kind of extension of this gigantic cluster of galaxies. The Virgo 2 group begins at the level of the M61 and NGC 4753 groups, which form the southern edge of the Virgo cluster. The filament then passes through NGC 4697 and NGC 4699. It ends 30 million light-years further on, with a group of galaxies centered on NGC 5084, a huge lenticular galaxy seen from the edge. M61 is one of the most remarkable galaxies in this long filament of galaxies. Located on the southern edge of the Virgo cluster, this spiral galaxy seen from the front was discovered by Italian astronomer Barnaba Oriani in 1779 and observed on the same day by Messier, who initially mistook it for a comet. It is also one of the largest galaxies in the Virgo cluster. It is also a star-forming galaxy. 8 supernovae have been discovered in this galaxy to date, the latest in May 2020. The M61 group comprises at least 32 galaxies. NGC 5084 is another remarkable galaxy in the Virgo 2 groups. With a diameter of between 250 and 300 million light-years, this lenticular galaxy is gigantic. In fact, it's one of the most massive galaxies in the Virgo supercluster. Its mass is more than 10 times that of our own Milky Way galaxy. The Virgo 3 groups form a long chain of galaxy groups to the left of the Virgo cluster. It spans more than 40 million light-years. Why such a long distance? It seems that the gravitational pull of the Virgo cluster has contributed to the stretching of this chain of galaxy groups. Astronomers have estimated that the Virgo 3 cluster comprises 8 galaxy groups and 13 galaxies outside these groups. Among the galaxies in the Virgo 3 groups is the spiral galaxy NGC 5248, which is one of the brightest in its region, and the brightest in a small group of galaxies. It has a special feature that has been observed by the Hubble Space Telescope. Around its nucleus are not 1, but 2 star-forming disks. NGC 5364 is a spiral galaxy with very long spiral arms. This feature allows it to be classified as a grand-style spiral galaxy, a title deserved by only a tenth of spiral galaxies. This galaxy is beautiful to look at, even if its spiral arms are slightly asymmetrical and distorted, certainly due to interactions with a nearby neighboring galaxy. Let's continue our exploration of the Virgo supercluster with the elliptical galaxy NGC 4697, located in the Virgo constellation some 40 million light-years from Earth. NGC 4697 is an active galaxy with a faint core. According to a 2008 study, it contains a supermassive black hole of around 170 million solar masses. It is also home to numerous X-ray sources and is surrounded by a halo of hot gas. These characteristics suggest that this galaxy has had a turbulent past, with supernovae, black holes, and neutron stars belonging to binary star systems, all of which could be the origin of X-ray sources. In fact, a large number of X-ray binaries have been discovered in the galaxy's globular clusters. What's more, since black holes and neutron stars are the final stages in the life of a massive star, astronomers believe that this galaxy was home to many massive stars in the past. The NGC 4697 group includes at least 19 galaxies, including the barred spiral galaxy NGC 4731, which measures over 80,000 light-years across. Its spiral arms contain a large number of young blue star clusters. You may notice that its spiral arms are distorted. This is due to interaction with a giant elliptical galaxy called NGC 4697. In the NGC 4697 group, you can also see a small spiral galaxy called NGC 4775, which also has deformed spiral arms, in addition to an off-center nucleus, and the barred spiral galaxies NGC 4941 and NGC 4948. In the Hound Dog constellation, you can see a vast spiral galaxy whose nucleus is surrounded by a star-forming disk. This is NGC 5033. This magnificent galaxy would have a perfect shape if it hadn't crossed paths with another galaxy during its history, slightly distorting its spiral arms. Its active Seifert-type galactic nucleus is particularly bright, and is certainly home to a supermassive black hole that absorbs large quantities of matter. The brightness would then be due to the hot gas in the black hole's environment. Observations of this galaxy have shown that the location of the active core does not correspond with the galaxy's kinematic center, i.e. the point around which the galaxy's stars revolve. This would mean that the galaxy has certainly undergone a merger. This shift is certainly the primary cause of the core's brightness. Indeed, the shift between the nucleus and the kinematic center can destabilize the rotation of the gas at the galaxy's center, causing the gas to fall into the nucleus. The gas is then compressed by the enormous gravitational forces of the core center and becomes hot. NGC 5033 forms a pair with another galaxy called NGC 5005, but they are not close enough together for gravitational interaction to cause tidal forces and distort the galaxies. The gravitational interaction between these two galaxies remains fairly weak. In any case, we know that NGC 5033 is part of the NGC 5005 group, along with other galaxies. Astronomers disagree on the number of galaxies in this group, but there could be between 4 and 16 members. Let's continue our exciting journey into the heart of the Virgo supercluster with an exploration of the Hunting Dog Cloud. Also known as the Dogs 1 group, the Canes 1 group, or the M94 group. This cluster of galaxies spans the constellations of the Hounds and Bernice's Hare. It doesn't contain many noteworthy galaxies, so it's only very recently that we've been able to distinguish this group from the many other background galaxies in this region of the sky. In fact, it contains mostly medium-sized dwarf galaxies, ranging from 5 to 25,000 light-years in diameter. The largest galaxy in the Canes 1 group is the spiral galaxy NGC 4244, with a diameter of 65,000 light-years. This galaxy is seen from the side. Spiral galaxy NGC 4395 is a good example of a Seyfert galaxy, with a very bright core and faint spiral arms. However, it remains very faint and therefore difficult to observe. In the Dog 1 group, you'll also be able to observe NGC 4214, a small, irregular, hydrogen-rich star-forming galaxy of interest to astronomers because it contains stars in various stages of formation. Observations of this galaxy have shown complex patterns of glowing hydrogen formed during the star birth process, but also clusters of much older red supergiant stars. Before continuing our journey, let's take a look at the spiral galaxy M94, which gave its name to the Dog Group 1, also known as the M94 group. It lies at the far end of the cluster and has a diameter of 30,000 light-years. It's a star-forming galaxy that's magnificent to observe. Yes, not only is it seen from the front, but it also boasts a beautiful ring of bright blue stars and well-defined spiral arms. In any case, astronomers haven't yet tired of observing it, and are currently trying to unravel the mysteries of its starry outbursts. The Hunting Dogs cloud should not be confused with the Dogs 2 or Canes 2 group, which lies behind it. Also in the Hounds constellation, this galaxy cluster contains a remarkable galaxy, M106. Discovered by Pierre McCain in 1781, it wasn't added to Messier's catalog until 1947. And yet, this galaxy is particularly large and bright. It is 130,000 light-years across, larger than our own Milky Way. Its morphology is unusual. 2 spiral arms are clearly visible, detached from the rest of the galaxy, which is not very bright. The most precise images of this galaxy show that it may actually have 4 spiral arms. It is not known, however, whether these 2 additional arms are made up of stars or simply gas. In the same images, impressive jets of matter can be seen on either side of the nucleus, indicating that M106 is a Seyfert galaxy with an active nucleus and that it contains a particularly active supermassive black hole at its center. The galaxy NGC 4217, often presented as a companion galaxy to M106, appears smaller, but is in fact of equivalent dimensions. It's simply not as close to us as M106. However, it's not certain that it's really a companion to M106, or even that it belongs to the Canes 2 group, as some measurements estimate it to be 60 million light-years away from us, further from M106 than it is from the Milky Way. We're now in the Lion constellation. You're looking at the Leo 1 group, which is made up of 3 subgroups. On the right, the M96 subgroup, and on the left, the M66 group, and in the middle, the galaxy NGC 3489. The M96 group includes M96 and M95, 2 barred spiral galaxies, and NGC 3377, an elliptical galaxy. All 3 are particularly bright. M96 and M95 were both discovered on the same evening, March 20th, 1781, by Pierre McCain. They are slightly smaller than our own Milky Way. Both feature an inner star-forming disk close to the nucleus, whose secrets astronomers are trying to unravel. In particular, the links between these disks and the central black tower and spiral arms. Let's take a look at the M66 group. It's also known as the Lion Triplet. It includes galaxies M65, M66, and NGC 3628. Their magnitudes make them easy to observe, especially M65 and M66, which are often photographed together, making the Lion Triplet the most beautiful group of galaxies in the Lion constellation. M65 is a spiral galaxy, and M66 a barred spiral. As for NGC 3628, it's a magnificent spiral galaxy seen from the edge, with clearly visible dust bands. We can also see a trail of stars that have been torn from it by the gravitational forces between the three galaxies. In the past, interactions between NGC 3628 and M66 strongly affected the morphology of M66, which now has a more elongated spiral arm and a more diffuse halo. NGC 3489 is located in the Leo 1 group, between the two subgroups of M96 and M66. This lenticular galaxy interests astronomers for its hybrid characteristics. It has a prominent galactic bulge and a visible central disk, like spiral galaxies, but no spiral arms. It also borrows characteristics from elliptical galaxies, with little ongoing star formation and stars over 1 billion years old. Like many of the galaxies in the Virgo supercluster, it is a Seyfert galaxy with an extremely bright core and a central black hole that devours any matter approaching it. The radiation from its active galactic nucleus, however, is weaker than average. See that vast gathering of galaxies to the right of the Virgo cluster? Those are the Leo 2 groups. These groups of galaxies lie behind the Leo 1 group and are spread over 30 million light-years. The elliptical galaxy, NGC 3607, is the brightest in the Leo 2 group. Among the other brightest galaxies in this area of the sky, you'll also find NGC 3169, a highly distorted spiral galaxy. It can be seen in the Sextant constellation, just below the star Regulus in the Leo constellation. Gravitational interaction with its neighboring galaxy, NGC 3166, has taken its toll on its magnificent spiral shape, and it now looks as if it's completely disintegrating. Astronomers wouldn't be surprised if the two galaxies were to merge. In Leo groups 2, you can also observe a curiously shaped spiral galaxy, NGC 3187. It features very open spiral arms. As for spiral galaxy NGC 3227, it's glued to dwarf elliptical galaxy NGC 3226. Both are among the 338 galaxies listed in Halton Arp's Atlas of Peculiar Galaxies, under the name ARP 94. According to American astronomer Halton Arp, they are a good example of a spiral galaxy with an elliptical companion. However, there is nothing to suggest that they are in fact interacting gravitationally, especially as the distance between them remains relatively large, at around 9 million light-years. Let's continue our journey towards the Furnace Cluster. But before we do, let's take a look at a remarkable galaxy called NGC 2997. This grand-style spiral galaxy is located in the constellation of the Pneumatic Machine, a constellation you may not have heard of often since it's located in the southern hemisphere and is relatively faint. NGC 2997 was discovered by William Herschel in 1793 and lies around 55 million light-years from us, but is moving away from us at around 1,100 kilometers per second or 680 miles per second. This galaxy is particularly remarkable for its nucleus, surrounded by a string of giant clouds of ionized hot hydrogen. The NGC 2997 group comprises some 15 galaxies, including several irregular Magellanic galaxies. Before arriving at the Furnace cluster, the Dorado group is also worth a visit. Call it a group, but it's more likely to be a cluster of galaxies given its size. The Dorado group comprises spiral and elliptical galaxies. It is organized around two interacting galaxies, the elliptical galaxy NGC 1549 and the lenticular galaxy NGC 1553. These are the two brightest galaxies after the spiral galaxy, NGC 1566, considered the dominant galaxy in this group. NGC 1566 and NGC 1553 are disk galaxies, which is the dominant galaxy type in the Dorado group. Astronomers therefore consider this group to be even richer than the local group. We're now looking at the Furnace cluster, the only other cluster within 100 million light-years of us that's almost as rich as the Virgo cluster, though still a little smaller. The Furnace cluster is of particular interest to amateur astronomers for its compact core of galaxies spread over just 2 degrees of sky. The two dominant galaxies in the Furnace cluster are NGC 1316 and NGC 1365. They're bigger than any galaxy in the Virgo cluster. NGC 1316 is a massive lenticular galaxy, which according to observations absorbed a spiral galaxy around 3 billion years ago. This was probably not the only galaxy to be cannibalized by NGC 1316. Not far from this galaxy is a spiral galaxy called NGC 1317, which could suffer the same fate. NGC 1316 is also a powerful radio source, known to radio astronomers as Fornax A. It is the most important source of radio waves in the constellation Furnace, and the fourth most intense radio source in the sky. These radio waves come from falling matter inside the supermassive black hole at the center of the galaxy, probably fueled by interactions with other galaxies. NGC 1365 is the best-known galaxy in the Furnace cluster. It is a magnificent barred spiral galaxy of great style. Discovered in 1826 by Scottish astronomer James Dunlop, it lies in the southern constellation of Furnace and is studied by numerous telescopes. Its bluish color is due to a very high rate of star formation. This can be explained by the presence of a bar that connects the two spiral arms and compresses the gas present in the galaxy, triggering the birth of multiple stars. The Eridan cluster is another remarkable galaxy cluster in the southern hemisphere. It is sometimes referred to as the Furnace II cluster. This is because it is very close to the Furnace cluster at a distance of around 20 million light-years. The Eridan cluster is further away than the Furnace cluster, at around 75 million light-years. These two clusters and their surrounding galaxies are sometimes referred to as the Furnace or Deep South superclusters. The Eridan cluster contains around 200 galaxies. Its galaxies are scattered over a larger area than in the Furnace cluster, so it is less impressive than its neighbor. Two subgroups can be distinguished, one to the south around NGC 1395 and one to the north around NGC 1407. NGC 1407 is a vast elliptical galaxy, larger than the Milky Way, with a diameter of around 243,000 light-years. Its group contains at least 9 galaxies. NGC 1395 is also a vast elliptical galaxy, but slightly larger, with an estimated diameter of around 264,000 light-years. The NGC 1395 group contains at least 32 galaxies. We can't leave the Eridan cluster without a quick look at NGC 1232, one of the most beautiful galaxies in the cluster, with its well-defined spiral arms. This stylish spiral galaxy is around 145,000 light-years across, and its spiral arms contain millions of bright stars, alongside dark dust, to the delight of our eyes. We've taken a tour of the Virgo supercluster. This trip will have given you a glimpse of all the types of galaxies that exist in the observable universe, with near-perfect spiral galaxies and spiral galaxies distorted by the movements of the universe, giant galaxies and dwarf galaxies, active galaxies, and galaxies where no stars are forming anymore. But you should know that the Virgo supercluster won't remain frozen like this for long. The universe may be moving slowly, but it's moving all the same. The Virgo supercluster itself is constantly changing. It is attracted by the Great Attractor, a gravitational anomaly located near the ruler cluster. But what exactly is the Great Attractor? The discovery of the Great Attractor dates back to 1977. American astronomer Vera Rubin and her colleagues at the Washington Institute discovered that the Milky Way was moving faster than the expansion of the universe. The astronomers hypothesized that there was a force with a gravitational effect on the Milky Way, without knowing exactly what it was. A team of 7 researchers from the Cambridge Institute of Astronomy and the Washington Institute of Astronomy was formed to investigate the question. For the record, this team was nicknamed the Seven Samurai. To unravel the mystery of this unidentified gravitational force, the researchers measured the proper velocity of a large number of galaxies in order to determine in which direction the Milky Way and the local group were moving. 400 elliptical galaxies in the Centauri region were studied over a 5-year period. In 1986, the researchers from this small team discovered that the local group, as well as the Virgo supercluster, were moving at a speed of around 625 kilometers per second, or 390 miles per second, towards a point they dubbed the Great Attractor. This point lies beyond the Hydra Centaur supercluster, in the direction of the Southern Cross, some 150 million light-years away. Scientists have calculated that the gravitational force of this mysterious attractor is equivalent to that of a supercluster, over 10,000 times the Milky Way. And yet, no visible mass has been identified. Here is a spine-chilling anecdote. Foucault's pendulum in the Pantheon in Paris points in the same direction, but no one knows why. An even more mysterious fact: in the region of the Great Attractor, the natural speed of galaxies is that of the expansion of the universe. And once past this fictitious point, galaxies have a speed slower than that of the universe's expansion, and some even show a blue shift. But the presence of the Great Attractor alone cannot explain these speed variations, In fact, other researchers have measured the radial velocities of galaxies in the Perseus and Pisces clusters, which are located further from the Great Attractor than the Milky Way. And it appears that they are drawn faster towards the Great Attractor than our galaxy or even the Centaurus or Hydra clusters located closer to this fictitious point. Researchers have put forward all kinds of hypotheses, including the presence of another Great Attractor or the imprecision of radial velocity measurements due to the uncertainty linked to galaxy luminosity. In 2016, after 30 years of research, researchers identified the existence of large extragalactic structures that could explain the gravitational attraction of galaxies towards the Great Attractor, without, however, completely solving the mystery. We've come to the end of our journey through the Virgo supercluster, but we're not done exploring the universe yet. The Virgo supercluster is part of a larger whole called Laniakea, and Laniakea itself is just one of the 6 million superclusters that exist in the observable universe. So there's still a long way to go before we understand all the mysteries of our universe and its organization. In the meantime, we can marvel at the beauty of galaxies and stars and the way they are arranged in the sky, whether by chance or not.